something from Epcot.
Which that has now been recorded, so.
So as long as you see that, that means it's recording.
Right.
That little red dot,
Well, the screen.
or that screen.
Yeah.
Yeah, fine. I'll flash your red dot. I guess you could stop and save it.
Go at the bottom left.
Just say, call. That you remember to call.
Do it from there.
Yeah, you'll have to do it from here.
1, 8, 6. Oh, you can see it on the screen.
Six.
469.
Welcome to WebEx. Enter your access code or meeting number followed by pound. Enter your attendee ID number followed by pound.
Hello.
Oh,
Hello.
Hello.
Hi, this is Mandy.
Hey, Mandy, this is Mike.
Hi, Mike. Can you hear me okay?
Yes. How about us?
Right. So you have a whole entire crew with you?
Small crew.
All right. Well, that's better than us, I guess.
Let me talk in a normal. Can you hear us now?
Yeah.
You need us to talk to make sure she can hear
I'm
us?
gonna go check the recording. I'll be
Okay.
I think she heard us initially.
Okay.
Okay. Can you hear Erica? Erica's got a soft voice.
Oh, sorry.
Oh, Erica, honey, you sound so far away.
No, I'm sitting right next
She's
to the
actually
phone.
the closest to you physically.
I should speak louder, I guess.
Okay. Can you hear us?
Can you guys see my blue screen with the mouse moving?
Yes.
All right. So you let me know when everyone's settled and ready. I heard somebody in the background saying they were going to get the recording ready.
He's going to check it. I just maximized the screen to the most we could do. Can you still move
Okay.
your mouse?
Yep.
All right.
Can we close the little box at the top with the now present?
Tooltip. Yeah.
Yeah, close the tooltip. Thank you. There we go. So now we can actually see the things that are there.
Okay. Yeah, we've got a IT person here that's going to help us with the recording. So,
Perfect.
where are you located?
I am currently sitting in Austin, Texas.
Oh, good.
Yeah.
Well, sorry to make you wake up.
Thankfully, today will not be too hot. I'm a northern girl, and this heat is it's too much.
I did my bachelor's and master's degree at Austin, Texas, at UT.
Oh, did you?
Yeah, it's a great place.
It's definitely an adventure. Yeah, I'm, one of the weirdest things for me down here is the road structure.
Yeah.
If you see where you want to go, you've already passed how to get there.
Yeah.
Like big loop-de-loops everywhere you try to go.
Austin's grown up quite a bit with all those bypasses and everything around out to the mall, and I know it's grown up since we've been there a bit.
Oh yeah, it's growing incredibly fast. They can't keep up with the number of people moving in, and the traffic is just getting worse and worse. So they're always trying to improve the roads, which, as we know, makes everything worse until it actually happens.
Mm-hmm.
Madness, sheer madness. And let me just tell you, I thought Ohio drivers were the worst drivers on the planet until I moved to Texas.
Oh, well.
And they tell me it's because of all the Californians that have moved here. I don't know what it is.
Oh, now you broke it.
Did I break it? I probably
It
did.
got really quiet.
You guys have entered a wind tunnel. Is everyone okay?
We were
We're
moving
okay.
around the
Sorry.
phone.
I
Can you still hear us?
probably broke it.
Can you hear us?
Yes, you sound kind of far away, but I can hear you.
What'd you do?
I kind of assumed that there was a directionality to the microphone,
All
but
right, hang on a second.
Maybe there is.
We're going to
I
play
was
with this
just
just
wrong
a
about
bit.
which one it was.
All right,
Okay, is this a good direction for the microphone?
can you hear us?
For whoever just asked that, yes.
All right, we're just trying to get this kind of figured out here. 'Cause I don't
Oh,
know.
that sounds better. That's loud. That's good. You're close.
Well, I
Not
was-
king candy.
It was
Right on top of
very
it.
Yeah,
close,
he was on top of the phone.
Okay, how about now?
Good.
All right. Okay, apparently we're recording fine, so go ahead and do your thing.
Okay, well, the first thing, I know everybody intends to use the instrument kind of in a different way, so there's a ton of features in our software, but I want to focus on the way that you guys hope to use it. So can you give me just real brief, I'm going to mostly collect spectra. I want to collect images and then spectra from that, or I want to do maps, or is everyone kind of doing everything?
All of those sound great to me.
Yeah, all the
Yeah,
above.
sounds
This is setting in a core facility, a service center. And so what we're going to do is get a lot of users with all of those different needs. We've got certainly
Okay.
just from the basic collecting a simple spectrum to, comparing spectra to, like you said, mapping. And along the way, we've got some questions about in terms of scanning an entire field of view versus,
Point and click.
sort of point and ID, on a small
Point scan.
pixel-sized point and those kinds of things. So,
We can do all that.
You guys all
So
right?
I'm going to give you a very broad overview just to start, just so you know what all these different things are on our software, and then I'll go into each kind of feature. I'm going to start with the basics because once we understand how we work with images in our software and how we work with spectra, all of the heavier, bigger features are built onto those basics. So our software kind of only gets easier once you understand the basics.
Okay.
So first things first is, this is just the basic toolbar that you guys have on your software.
Mm-hmm.
One thing you'll notice as you're learning the software, you can set your mouse somewhere. I'm not clicking, I'm just setting it there, and it's going to tell you what something is, so you can know what a button is before you have to, commit to clicking on it. So this also will help you learn the software. Now, right now, you can see I have no data open. I only have a few buttons available to me. I have, your new file, your open file, help, interactive help. All of these guys are grayed out. These ones that are not grayed out, these are our main functions. This is collect a new spectrum. This guy you don't have to worry about because you don't have XRF, because that's something else that we do in addition to EDS is XRF in the SEM. So you can ignore this button entirely. Camera, that's kind of obvious. That one's for a new image. And then we have map and line scan. So these are the core abilities. Now I'm going to go back to what I refer to lovingly as our creepy eyeball. When I click on that, that's our interactive help.
Mm-hmm.
So this is literally a wizard approach to help you figure out our software. You can always have this open, and it's like I said, it's going to be a wizard approach. So if I say, let's start with digital images, when I click on that, it's going to take me to the next menu. You'll see at the bottom, I always have my back button. So once you get familiar with the software, you're welcome to close this. You can leave it open, whatever suits your fancy. So I'm going to go over to my microscope. Unfortunately, with WebEx, I can only give you one of my screens at a time. So I'm going to leave us on the software. You're not missing anything interesting on my scope. I'm on a, Hitachi, what am I on today? The 3400. And right now I'm just looking at a simple nickel grid, mostly because I wanted to focus on software and not to all be crazy analytical scientists and try to identify what I'm playing with. So, the basics. Start with a digital image. doing is we communicate with your microscope. So when you ask it to grab an image, whatever your field of view is over on your microscope is what we're going to bring over. So if your image on your SEM is too dark, too bright, too blurry, not high enough mag, that's what we're going to bring over. So the first thing when you're doing images, make sure your image is what you want. Then you can acquire an image. And all I did was click this acquire an image button. And you can't hear it on my side, but it clicks. I've taken over the microscope. So my field of view on my microscope looks kind of like old school TV when there's no channel to tune in. And then it gives it back to control. So here we have our image properties. This concept of properties is going to go throughout our entire software. When I say properties of whatever it is, an image, a spectra, a map, that's how we're collecting our data. And then if there's, processing, like in a spectrum, if we're going to quantify, that's how we deal with that data. That's all part of our properties. So the basics with an image that you're going to want to focus on is your resolution. So I told you, whatever you have over on your microscope, we're just going to bring over. But there is a little flexibility with that. If you don't have the need or the patience for a full, 4x4 image, you just need a nice image, you can bring your resolution down. So right now, my microscope is at 574 times magnification, which is read up here. So at 500 mag, I had a resolution of about 512. You see, that gave me a pretty decent image. Mm-hmm. So you can pick and choose what works best for what you're collecting. The other things in this window, obviously there's a lot of stuff going on in our software. I'm not going to tell you every single thing that every single thing does because we'll be here for about 2 or 3 days. But I'm going to give you the main things you need to focus on to start getting good data. This sync to AC. This is something that you may need or may not. We have some labs that it will literally pick up the AC current of other things in the building or in the room. If you're seeing a horizontal line in your image, it may be that you're picking up that AC current, and this is where you can sync the collection of the image to get rid of that line. So the main thing from our properties is resolution. Also, you'll see we have here, you have your properties across the top. So if we wanted to not use our creepy eyeball, you could collect an image here, and you could look at the properties from here. But we'll stick with this for now. So now that I have an image, let's just talk about what we can do with just the image. We won't get into EDS just yet. Our image annotations, these are all the fun things we can do with the image. So because I'm talking to my microscope, it's reading my KV and my mag so that I can actually put down things like magnification, KV, micron bar, working distance. Because, again, we're talking to the microscope, these actually mean something. Of course, you can put a logo. Right now, you're defaulted to our logo. If you love us so much you want our logo, we love that too. That is, you don't have to keep our logo. So one thing to know about our software that's very important is everything in our software can be edited to your needs. So if you absolutely hate this shade of red, or if you need this to maybe not be in microns, you need it in a different increment, you can right click. So anywhere there's something in our software that you need to edit, first try right clicking on it and you'll get a new menu. So I'm going to come here to my micron bar and I'm going to right click on that and you'll see that opened up a separate menu. I'm going to bring that up so we can see it better. You can see here, this is where I'm able to change that color. I'm also able to change my units. Mind you, the units, if you're sticking with, metric, the units are going to be a function of your mag. So obviously you're going to be limited to, according to your mag, how big or how small you can force those units to go. It's going to, if you're zoomed way in and you're working with a beautiful high-powered scope and you're truly in at nanometers, it will default to nanometers. But we've had some customers that their customers want inches, so you can change that. Now, as good as notes as everyone takes, I don't expect you to remember everything that we see today. The main idea to remember and to take away is to have in the back of your mind that things are editable and that menus exist, and then you can always go on the hunt.
Yeah, good.
So this is a concept across the whole thing. Anywhere I right click, I can change what that looks like.
So you're right-clicking on the annotation bar itself as opposed to on the picture?
Correct.
Okay.
So I'm right-clicking where it says working distance. I'm actually right-clicking on the WD, and then I get that menu of what I can change. So these things may not be super important for you to change. You may be okay with the default red or whatever, but that just kind of segues us into that concept. So now I'm going to come up here to these tools. So I have my ruler annotation. I first left-click that, and now I come and I click where I want my ruler to start, and I drag it. When I've reached where I'm done measuring, I let go. So now it's measure an area for us. Now my microscope has been image calibrated so that I know that this is a true measurement. If you have NIST standards and you want to calibrate to a higher level of precision, we can talk about how to do that. But right now we'll just focus on what we can do with an image. So that's my ruler bar. I have an angle. If I left click on the angle annotation, and then I click where I want to drop that angle, you see I'm just moving around. And this kind of stuff you'll get a feel for once you sit down and start to play with it. But you can see right now I'm holding down my left button, and that's allowing me to move. When I let go, you see I get all these other squares. So when I have squares, that means something can be moved or edited. Obviously, when I have that big old 4 triangle guy, I can move the entire thing. And that applies to any of our annotations. We have the arrow, so I can point to a weird particle or whatever I'm trying to point out. This one here is the freehand, so when I select that, I can put my squiggles, whatever you're trying to do, and you see again, you get those squares that allow you to edit little portions at a time, or you can grab the entire thing and move it. So the theme for everything is the same throughout. I'm going to skip this one for now. We'll come back to it. I want to stick with the basic theme. We have our square or rectangle. Again, if you're trying to point something out or highlight it, circle or oval. This one here is a text box. So when I click on that, I come up here, wherever I want to drop it, I click and drag a box. That gives me my text box. So now you see I have my cursor, and I'm able to type in here. Once I type whatever I want, I click outside of the white box, and now this, just like everything else, can be grabbed and moved to wherever I want it. I double click to get my color and my font. And then also this last one here is our straight lines. So now I'm going to come back to this guy that looks like a big old cactus. When I select that, this one's kind of cool and fun. So what this allows us to do when we select that, it goes into my own file structure, my own folders, and it's going to allow me to select an image that I've previously saved. So let's say that you have a sample that you just have a photograph of, or maybe you looked at it first under a light microscope at maybe 5 times mag, and you have that image that you want to correlate to this higher magnification image. You select the image that you want, you say open, and then you click and drag wherever you want on the image, and it drops that image on there. Again, once it's here, I have full reign over it. I can move it, I can make it bigger, I can correlate it, put an arrow, this area is looking at this, or whatever I need to do. So what's important about all of these annotations is when this annotation toolbar is open, I have full editing capabilities. I can highlight something so I see my little marks on it, and I can hit delete to take it away. You see I can move things around. When I close my annotation, it's essentially burnt onto the image. When I come back and I open my annotations, again, full reign. So just from an image standpoint, let's say I love all my crazy marks that I've put on. I'm ready to come up here, and I can go to save. We are first and foremost going to make you save the file is our image file type, our .imx. The reason we do that is this is a true data file. So let's say 6 months from now, I realize, oh, I'm an idiot. I totally forgot what mag I ran this at and what working distance I was using. That's okay. It's a true data file. That's why we make you save it. But if you want to maybe email this to a colleague or put this in a report and you need it as JPEG or TIFF, you see down here at the bottom, we can automatically, anytime you save an image, automatically also save it as a JPEG or any file type you could ever imagine, and some you may have never even heard of or don't realize still exist, like WordPerfect, for example. You can save these images automatically. You can also have them go either with or without those annotations. So all those fun things we put on those are our annotations. You can even save one image as a JPEG with the annotations and then another without. Totally up to you, but there's full flexibility in how your images are going out. So that's just the basics of just getting an image, just labeling our good stuff from it.
Mandy, do you have to paste these annotations to the image, or do they just get saved that way automatically?
So when you are doing the save and you do the export with annotations, it's going to go automatically. I'm sorry, was that what you were asking?
Yeah, because like in other software that I have in the lab, other image capture software and something like Photoshop, you've got to physically paste it or flatten it to the image to get it to stay. But you don't have to do that as an extra step.
Nope, it's very straightforward. So let's say I just wanted the image as a JPEG because I'm going to send it to a colleague and I want maybe their ideas on what they want to point out or what they want to add. If I take away the annotations, it's just going to go as a naked, clean image.
Okay.
If I say with annotations, it's going to go exactly as we're seeing it right as we've done it now. So it's just one extra click. You don't have to do anything special.
Okay, great.
So there's a few more things we can do with image. I'm just going to close this guy and grab a clean image just so we don't have to see all my crazy marks. So you'll see here that we have image adjust. So that was part of our properties. But when we're talking image adjust, if we go to the display, let's say you have a wonderful, very well-meaning new undergrad that grabbed a whole bunch of images for you, and now that sample's been moved, and you don't have time to get back on the microscope. Somebody else is using it, but God love them, they didn't make it bright enough, or whatever it is. You have the option with the display to kind of do some post-processing where you can change the contrast or the brightness to your image. Just so you know that that's kind of there for a worst-case scenario if you didn't grab the image that contrast that you wanted from the beginning. Also, we have image segmentation. So this is kind of a throwback to when people were using or focusing on backscatter to get an idea of Z. So when we're using backscatter, you guys know the grayness means something. It applies to the Z. So you can actually, if I were using backscatter in this case to grab this image, I could assign colors to the levels of gray. So that's what we're calling segmentation. I don't know if this is something you guys will ever need. I just wanted you to know what it was when you see this button. So if I am using my backscatter and I want to assign different amounts of gray, I just select the color and highlight the grayness on my histogram scale here. So just kind of know what that button is. You may never use it because you have a real live EDS detector, so you can do real math to know what those elements really are versus just guessing according to Z. Mm-hmm. So this one here, this morphology, I don't know if you guys do any basic or full-blown particle analysis or have any aspirations of doing so.
We haven't so far. I don't know if we've had the ability to do it, so.
Okay. So, again, with anything that I say, please forgive me if you guys already know this. I mean no disrespect. I just to make sure everyone's on the same page when I describe things. But when we say particle analysis, in the industry, that literally means find my particles, count them, measure them. That could be diameter, perimeter, whatever settings I ask you to measure, and then also do the EDS analysis. So that's considered full-blown particle analysis. Count them, measure them, tell me what's in them. Just so you know, for future reference, if you guys want to dive into full-blown particle analysis, that is something you already own within our software. It's not a separate piece of software you'll need to buy. It's something you will need a little bit of hand-holding just to get started, but that's okay. We're fine doing that for you. But just know, if you want to do that, that is available. When we say full-blown particle analysis, that could be a single field of view, multiple fields on a single, we'll call it sample stub, or if you have a carousel, multiple fields on multiple stubs. Do you guys have an automated stage on the microscope you're using?
Yes.
Perfect. You're more than halfway there if you want to do
Yeah.
hardcore full-blown particle analysis.
Good.
If you just want to do kind of a quick and nerdy basic, what we'll call particle analysis, we have what's called morphology. So you don't need to go into that heavy lifting program. You can just do something kind of quick and easy.
Mm-hmm.
So this is what it is here, our image morphology. When I select that, you'll see that I get my histogram, again, that grayscale of what's going on with my image. So generally, when we're doing particle analysis, we want our particles of interest to be white against a black background. It's more common for people to use backscatter when they're trying to do particle analysis for that exact reason. It's easier to make your particles glow against a dark background. In the interest of saving time and switching out samples, I'm going to cheat. I'm going to use my grid. So what we want, again, white particles against a black background. If you have a sample where it's close but not perfect, this is where the histogram allows you to change that. So I can come and use my right and left mouse buttons. So I'm using my right mouse to make this all red. I'm going to use my left mouse just to highlight, and we'll see what happens when I select apply. So now I have my white particles against a black background. Again, because I'm cheating, this is a little more, convoluted. When you have real particles, it should pretty much be already white against black. This just allows you to tweak it a little bit. So again, because we may not be able to get a perfect grayscale white against black, we have the option to dilate and erode away things that we know may not be of our particle, but when you image a carbon stub, sometimes you get those weird curves of the holes in the carbon sticky or the carbon stub.
Mm-hmm.
So we can allow you to erode that away. Once I've switched this to black and white, we're working in pixels. So you can see I am pixelated. Do we see that? I don't know if your screen's big enough to see that these are kind of pixelated.
Yes.
Okay, so this is what we're talking about with dilate and erode. So because I know what's going on with my sample, I can say, I know that some of this is background, it's not my particle, so I want to erode that away so that it's not counted as a particle. So if I click erode once to get those little particles to go away, we'll say twice to get some of those other little ones. Now if I dilate back up 2 times, from a pixel standpoint, I'm back to my original measurement. So now I'm actually measuring my particles the way they need to be measured. If I have 2 particles that I know are separate, but they're kind of butt up against each other, and I want them to be counted as separate particles, we have our manual editing. So I can go to line or freehand, line would be straight, and I can draw to separate these particles to assure that they'll be counted as 2 separate particles. So if I just want to count them, let's say you have a filter with a whole bunch of schmutz on it, you just want to count how many particles are on there, you can go to label. And it's just going to go through and count them all for you. If you actually want to measure those particles, we can go to setup. And here we have a whole beautiful smattering of image analysis features. So just so you know, all of these are defined within our manual. And I'm going to pause there while we talk about manual. I, like everyone else in the world, hate manuals. I hate reading them. They're a pain in my booty, and they're usually not helpful. Ours is actually helpful, and the best part is if we come up to help, well, I have to close that to get there. Help topics. This is our entire manual. I don't expect you to sit here and read it, but what I love about our manual is obviously we have the different, chapters, but it's searchable. So if there's something you're looking for, you remember that I mentioned something, you remember a keyword, you can look for it, find it quickly, and it walks you through things. So we have feature analysis. This is exactly what we're looking at, and it shows you screenshots, all the good stuff. So our help is actually helpful, but in our manual, with this setup, it tells you what all of these features mean. And if this is something that you guys think you're kind of interested in, I can send you some easy documents to help walk you through stuff after today's discussions.
Yeah, we may want some extra help with that. So.
Sure, great. I have all kinds of documents I can shoot you guys at the end of today, and you can disperse it and share alike of all the things that we'll cover that'll be more boiled down.
Good.
And this will be one of them. So once we have, I didn't mean to close out of there. So once we select the features we want, I want area, perimeter, diameter. If I go to criteria, I can just across the board measure everything and get all of that data. Or if I know I'm only interested in the smaller particles, I want to ignore those bigger guys or vice versa, I can set limiting factors. So I can set my minimum, my maximum, and apply those limits. Right now, we'll just do them all. So once I've done my setup, now I'm ready to measure. I select measure, it's going to go back through, it's going to count them, and it's going to measure them. So it gives us this data here. Another important thing to know about our software is we are Windows-based. So that means a few things for you. One, saving file structure, all that stuff, it's what you're used to. That makes life easy. We don't do something weird to you from a saving standpoint. But also, everything in our software transfers easily out into things like Word, PowerPoint, Excel, Publisher, email, whatever you're doing. So you see here, we can put this to the clipboard, and that would allow us to drop that straight into a Word report or straight into Excel. So this data is really easy to just get out. Or, of course, you can just print it, whatever makes you happy.
Mm-hmm.
So we've counted our particles and we've measured them. We're halfway there for what we consider particle analysis. I'm going to show you a cool trick. It's one of my favorite things. So I'm going to close this guy. I'm going to go to Setup Analysis Position. So that's across the top, Setup Analysis Position. Now I get this new window. You'll see here I have some options. I have Add labeled. So that just brought over all of the X and Y coordinates of every single particle we just found. And now this would allow us to collect EDS data from all of those particles. So we've taken, we lovingly call this poor man's particle analysis because we've counted them, measured them, and now this allows us to get that EDS data. So I'm just going to briefly touch upon this because we can come back to this window once we learn more about how we work with spectra. But again, kind of keep that in the back of your mind that this is something you can do if you have a single field of view. You just quickly need to count a whole bunch of particles and tell me what's in them. This is perfect. This window can even generate a report for you when it's done collecting all of that data. So we have almost 50 particles. It would list those 50 particles similar to what an Excel spreadsheet would look like. Particles down the left, across the top, whatever elements you've asked it to identify, and then their associated concentrations. And we can come back and look at this as we build on spectra.
Can you define the points manually that you wanted to look at?
Yes, that's where I was going next. So we'll go there next. So first, let's go back to this morphology for a moment. So let's say you've defined your particles, but this is a really ugly image. Now I don't even know what I'm working with anymore. You see our undo down here. Our undo can be for when you separate particles or, as you're doing one step at a time, you can go back one step. You're seeing my dilate and erode or working backwards. But this also allows you to come back to your original image after you've done your analyses. So if you want your original image with all of those points marked and the data, that's how you get back to it, is that undo. So now, to answer your question, I'll just grab a new fresh image. Again, just we don't have to deal with all that. So I have a clean image. I go to my Setup Analysis Positions. I have a nice clean slate. You see here I have two options in the upper left, and we also have these up here, and I'll show you what we're doing with those. This guy is just to drop one point, so I can drop points all over the place on my single field of view. And this guy is to draw rectangles or squares that will raster. So I'll raster that area.
That's the point ID.
So yes. And this is just for, like I said, this is just for a single field of view. As we go on, I'm going to show you that because you have that automated stage, we can also drive all over your stage and do a whole bunch of stuff. We'll see that later because, like I said, I just kind of want to build on things as we go. But yes, you can do that. This way you can set up a whole bunch of stuff in that field of view, go get a cup of coffee, check your email, come back, have data waiting for you. So we'll come back to this window on how to work with that. So let's back. So let's say I have a sample where I have a lot of things, I want to grab a few different images, a few different spectra, but I want them all to have the same prefix because this is a sample name or a lot number, whatever you're working with. You come up to File, Set Sample Name. So now everything I collect is going to have that prefix. That's going to make my life easier when it comes time to save all this. I don't have to type in a big long lot number 10 different times and chance messing it up. So I'm going to come up here, or I could do it from here. I'm going to grab an image. So now we have an image. You'll see these are still our main data collection tools. And these guys are all grayed out, and then I have some here that are available. Our software is going to try to lead you down the path. Right now, I'm on an image, therefore I only have my image tools available to me. These are EDS data from an image. These are all spectra tools, that's why I can't play with those. Those are grayed out. So this one here is spot mode. I grab this, and I can put it wherever I want, and it will go ahead, take my E-beam over, and collect data from that spot. So I'm going to minimize so we can see our two windows at the same time. So while this data is collecting, that spot is green. Makes sense. If I wait for it to run its full time, or if I stop it, it's going to go red. And we're going to get into collecting data and spectra and all that, but right now we're just kind of getting the concepts of what can be done from a data standpoint from an image. So we just did our spot. Now we have our square or rectangle, so we can grab that, and you see it's going to raster in that area. It's rastering in there, it's green. When I stop it, it goes red. Now also you'll notice my image name is Mandy's Lot 5-1, first image I've taken in this lot. My spot 1, if I come to the spectra, it'll be 5-1-1. That way I know this spectrum belongs to that spot. If I come here, this spectra -2 belongs to that spot. So we kind of, again, help you keep your data organized. We have the free, I'm sorry, was there a question?
Oh, no, I was mumbling about something else.
Okay. Mumble away. And if you have a question, holler at me.
No, it was not derogatory. It was, I was just saying I didn't get any of this explanation when we did the install.
Oh, well, I apologize. I will ask our installer to change his approach.
Oh, no, I don't want to get him in trouble. I just...
No. Well, that's the thing is because I'm the one that does the hardcore training. Our engineers, obviously, their main goal is to
Right, and that's what it was.
Overview, give you some time to play with it, and then, we roll in with the heavier lifting training. But feedback is good. I don't know what he's doing unless somebody tells me. So he's not going to get yelled at, but it's good to know. Unless you tell me, I don't know what he's doing out there.
Yeah.
I would love to be a fly on the wall, but
he went over some of it, but not, like I say, they did the install and we sort of got this brief, I got this brief overview. Anyway, this is good.
Feedback is great. Thank you. I'll let him know that he needs to kind of take it. It's a lot of information. So he needs to take it a little slower, maybe.
Yeah, you're
Thank
fine.
you.
Yeah.
So, all right, carrying on. We just did our spot, our rectangle, and we have one more. This is freehand. So I have a weird funky particle going on. I want to know who he is. If I have any finesse with the mouse, I can draw right around him. And it's going to collect just in that area. Again, we stop it. It goes red. That's 3. We have -3. Now, you'll see we have 2 more options here. This one is map on image and line scan on image. So later in the training, we're going to go really deep on maps and really deep on line scans. But I just want you to understand that there are two ways that we do maps or line scans. So we have this field of view, and I have all kinds of different data that I want to correlate to each other. I want it all in that same field of view. So if I only need to map a small area because it's an area of interest and I want it to correlate to that data, I can draw a rectangle and only map a small portion. Now, you are not limited to just mapping small areas. If I come back over to the left, what we call a fast map is going to map your entire field of view of your SEM, and it's just going to be a standalone map. And that's okay too. But I want you to know that those things are available from an image as well. Again, if you need to correlate data. Same concept applies to a line scan. I want to correlate this data to other things in this field of view. I click that, I draw my line. It's going to bring over that image, and then it will collect a line scan. Same concept with the line scan. If you don't need to correlate to all this data, you can do the standalone line scan. It doesn't need to correlate to anything, and it's just going to grab your entire field of view. So the main idea is when you just want to correlate data. So we have collected a lot of data here. Maybe we're not ready to process it. It's Friday afternoon, and I have a date with Hulu and my sweatpants. But I've just run a whole bunch of stuff. I don't want to have to come back on Monday morning and find 10 different files to process and work with. So we have this great tool here. If we go to File, Save EDS Data Set. When I select that, you'll see at the bottom, it lists all kinds of stuff. All of this good stuff are all of the different file types and tabs that I currently have open. So if I want to save all of them, I can leave all of them highlighted green. Or I can pick and choose which ones I want to save. So I can save these guys. Now, this button I clicked up here, this one right here, this is close all. So again, it's going to show me everything that's open. It says, do you want to save all or close all these guys? Yes, I do. All right. Weekend has passed, Monday morning. I'm ready to process that data. I come to open. You see my file type. I want to look for my EDS data set. There's my demo stuff, very fancy and official name. I open that, and it's going to open all of that data for me. So essentially what we're doing is instantaneously creating a file and putting it all in there for you. And now, as you can see, I have all of that data back and available to me, and I have free reign. It's all the raw data files. I just didn't have to go and save all of these files individually. Now, absolutely, you can save them individually if you want. That's totally your prerogative. It's just an option. It's an alternative way to save your data. Because I have had some customers get kind of hung up on this EDS data set. You can use it if you love it. You don't have to. You can save things individually one at a time as you're creating those files. So it's however you want to use the tools.
Can this, while you're mentioning that, is there a way for one of my users to capture a data set and then go post-process all this on their own computer?
So to do that, you would need a secondary software key of ours,
Okay.
Because that's how we control our software. I don't know if you've noticed, maybe in the back of your computer, there's going to be a little software key. It's probably purple. You may not even notice it. It looks like a little USB drive.
Okay.
That's how we use and protect our software. So yes, that absolutely can be done. If that's something you're interested in, we can discuss getting you another software key.
You know an average cost of that?
I don't even want a chance being wrong and lying to you.
Okay.
I can find out for you. Because that's why I am the scientist. I'm not sales. I'm sorry.
Yeah, no, I'm just curious if it's hundreds of dollars or thousands of dollars or whatever it might be.
The price varies according to what kinds of quantitation methods you need. So it's not going to be thousands because you guys don't have XRF. That's where it gets expensive because XRF quantitation is a bit more heavy lifting. Mm-hmm. So no, it's not going to be thousands. So rest assured. But I don't know exactly how much it is according to what quant methods you guys have. Okay. I can, after we're done here, I can have them pull up your file, and then I'll tell me what kind of software key you guys do have. And then I can also let you know from your file what that would cost to get an extra one or two or whatever.
Yeah, if you could, thanks.
Yeah, absolutely. I'm going to write that down as the memory of a goldfish. Software key. Okay. So the basics of collecting your data, if you like grabbing spectra from an image like this, pretty straightforward. Once you've collected the data, as you see, we have the data as spectra as standalone data files that we can work with, which I'm going to dive into next is how to work with spectra. Another thing that I found sometimes customers get hung up on is they think they always have to grab an image, then put down a spot to get a spectra. That is not the case. If you're looking at something relatively homogeneous, or you just have a big old hunk of steel, you know what it looks like. You don't need an image, but you do want a spectra. All you need to do is whatever your field of view is over on your SEM, is zoom in, fill that with what you're interested in getting EDS data from, and then come up here. We have new spectrum, or if you're doing the wizard approach over here, work with spectra, acquire a spectrum. So they're the same idea. When I select that, it's just going to raster my beam over my entire field of view of whatever is happening on my SEM. So that's what's collecting right now. So again, two ways to get our spectra. If you want to pinpoint from an image, great. If you don't need to, because it's just a big old blob of something, whatever your field of view is, just collect a new spectra. So before we dive into spectra, I want to give you guys a chance, if you have any questions about what's going on with images or how we're putting these things down, or if there's something you need to know about images before we move on to spectra. Silence in the room, is that a good thing or a bad thing?
Anybody?
I think we're good.
I think, yeah.
In a minute, I want you to, because we haven't talked about it yet, and it seemed to be one of the first things they talked about, was just at the top in terms of lifetime, time constant, your counts per second, your percent dead time. Will you go over that later?
Absolutely. I want to make sure we're comfortable with images first, and then we'll dive into all things spectra.
Okay, thanks.
Sure. So we're okay with images?
Yeah.
Are you okay?
All right, game on.
All right.
So I'm going to just close a whole bunch of stuff because I hate a busy desktop. I'm going to close all those guys.
Wait, how do you?
This is the close all button. It's the one right next to the eyeball.
It's this guy here. It just got grayed out because I took them all away.
Yeah.
Somebody's taking notes.
Paying attention.
I like that button.
You like that button?
So right now I just have my nickel grid, and I want to know what's going on with the whole thing, so I'm not even going to bother with an image. I'm going to go ahead and hit my new spectrum or acquire spectrum, but like you were asking, let's go across the top. My preset. That's how long I want to collect my data. Right now I have that set for live time. You can set that to also be total counts for the entire spectrum. It is more common and, in my opinion, more useful to stick with live time, but know that that option exists to use counts, and that will be, again, for your entire spectrum. So right now I have it set to 60. I'm impatient, and we have lots to cover, so I'm going to lower this just to 15. In real life, I do not recommend that, but that'll work for us for now.
And that's
So live time,
that's in seconds?
when we hit, I'm sorry?
That's in seconds?
This will be in seconds, but as we go across, you'll see what that actually means when we talk about live time. So this will be our live time counter. We'll see this counting up. This guy here is our dead time bar. So right now, I'm hanging out at about 10 or 11% dead time. That's why I'm green. As I start to creep up on 50%, I'll get closer to like a yellow. And as I get above my 50%, closer to 100%, I'm going to go red. So again, I don't know different levels of EDS experience in the room. I mean, no disrespect. You guys may be experts, so forgive me if I'm telling you things you already know. It is important to keep your dead time below 50%. Generally, a good comfortable range is, 10 to 20. You could even nudge up along 30%, but below 50% is imperative. Because if you have too much dead time, not only are you losing some data because you're not able to process that data, but you're also increasing the chance of producing what we call artifacts, which we can cover in a second. So we'll come come back to that, but I want to keep going across the bar. So right now you can see my counts per second. That is a function of what I'm hitting my sample with over on my microscope. So just for talking points, right now my probe current is at 62 over on my microscope. Depending on what brand microscope you have, that could be probe current, that could be just current, that's
probe current,
size.
probe current right now.
I'm sorry?
What's your probe current right now?
My probe current is 62.
62
My
what?
excitation is 20 keV.
Okay, the probe current is what unit? Is it picoamps?
I'm not sure what it is. I think so because they use it as spot size too. Hitachi uses probe current. Joel, I think, uses spot size. So they all use different
Okay.
words.
Because
to
spot
describe
size
essentially the
isn't
same thing.
going to have a unit after it, and probe current's going to actually have an amperage to it. So, okay.
So the way Hitachi shows it, it doesn't show a unit to it on their official screen.
Okay, so it's spot size. then.
Because they consider, again, Joel and Hitachi and Zeiss and everybody uses a different word for the
Yeah.
same thing. But
Okay.
obviously, decreasing and increasing that is going to change your counts per second.
Okay.
And then my mission current is in microamps. And then that's obviously a function of how my filament's working and what's going on with all that good stuff.
Okay.
So as we keep going over, we have our time constant. You guys have an SCD or silicon drift detector, which is a dry detector. They are capable of collecting a lot of counts quickly, much faster than the old silly or the liquid nitrogen detectors. So they can handle the lower time constants. So when we're talking time constant, we're talking in microseconds. How long we're the processing rate of our detector or our electronics for our detector.
We've got an older Oxford silly detector that's cooled with liquid nitrogen.
Okay. So what you guys are going to want to do is work in these higher numbers, or they're considered a slower time constant. I'm currently working on an SCD, so when you see me working at 4, that's because I have a dry detector. But for you, the 32, 16, 8, and 4 are going to be very good settings for you. Now, sometimes with old silly detectors, you may have one time constant just no matter what you do. It kind of looks junky. That's okay. As long as you have one good working slow time constant and one that's a good working faster time constant, you'll be able to collect maps and it'll be no problem. So the main thing is understanding what the heck time constant means is how quickly you are processing those incoming X-rays. And this is where it gets fun and twisted and slightly incestuous because all of these factors affect each other. So your time constant is how quickly you can accept those incoming counts. So right now I'm at 4, time constant of 4, about 9,000 counts, and a dead time of about 10%. Now watch if I change my time constant to 1. I'm waiting for my electronics to click. My counts changed a little bit, probably because I have some noise that I didn't clear out with my calibration. Let's find another one that was calibrated better. So essentially, the faster your time constant, the lower your dead time, because the more counts you can accept. So we'll bump it back up to 4, and you'll see my dead time jumps back up. So when I say a slow time constant for you guys is going to be 32, you're probably going to have a high dead time, but a slow time constant is going to give you better resolution. So all of these factors are going to be a function of what your main goal is. You need fast capabilities because you're collecting map and you don't want it to take 3 days, or do you need a nice slow collection because you're working with a lot of different transition metals and you need good resolution between those peaks. So that's what we're working with here. Now, going back to live time, we call it live time and not real time. This is the fun part because live time is a function of your dead time. So let's say that I'm running at a 50% dead time. That means half of the time I am not able to process incoming data. So if I set my preset to be 30 seconds live time, but my dead time is 50%, it means that those 30 seconds live time in real time are actually going to take twice as long. Therefore, it'll take me 60 seconds to run whatever I'm running. Does that make sense to everyone?
Yeah.
Yep.
All right, fantastic. So that's what we have going across the top. Now, let's play with some spectra. I'll bump this up just a little bit, give us some counts to work with. So I'm just going to grab a spectrum, let that collect a little bit. So once you have a spectrum, we give you a few tools to help you label your peaks. Easy enough if you kind of already have an idea of what to expect in your sample. We go to identify elements. We have your periodic chart. You know what's in there. You just select them and slap on those labels. If you are not sure what you're working with, or maybe you have some students that you're teaching and you want them to learn how to do this, when I click on my spectrum, you're going to see on your screen a green line up here. That is our cursor. Our cursor is a multifaceted tool. First, if I hold with the left button and drag to the right, you're going to see I'm zooming in. If I drag left, I'm zooming out. If I pull up, I'm pulling the spectrum up and down. Pretty easy peasy. If you don't like that, which some people don't, that's okay. You can do the same thing up here with our vertical expands and horizontal expand and compress. I prefer the cursor, but whatever makes you happy. So pay attention to the bottom. We have these squares here with the different elements. As I use my cursor to zoom in, those are going to get more spread out. These are K-alpha markers. So they're not saying an element is there. It's saying if a peak is sitting above a box, it could be that element. So I can select nickel because I have a peak sitting there. I do not have a peak there. So kind of just hold your hand a little bit on labeling those peaks. That's the second way to label. A third way, so I'm going to zoom in a little bit more. You can see my individual energy channels. Put my cursor in the middle, come to the bottom left. See it says cursor, and it tells me exactly what energy I'm at. If I come to the right, it's going to tell me at that exact energy what my options are. So if I move using my arrow keys on my keyboard, I can move one channel at a time and see those options change. When I see something that makes sense or I just want to try out, I can double click down here and you see it labeled for me. And I can come back. If I don't like something, I can double click and take it away. That's our third option. Fourth option, and one of my favorite ones, is we come back to our periodic chart, and you'll see at the bottom, it says scrolling peak identifier. So this is helpful when you're working with a new sample, you have absolutely no idea what's in there, or if you have a really complicated sample with all kinds of crazy stuff going on. I'm going to use my cursor. Wherever I put my cursor is where we're going to start in the identification. So I'm going to start at the beginning. So I put my cursor down here. I select enable. You see up here nitrogen turned yellow. That means that's where my cursor is at. When I come here, I have the arrows, and I'm literally going to scroll through the periodic chart. When I see something that makes sense and fits, I can select add, and now I can keep scrolling. So with just a nickel grid sitting on aluminum, this is kind of underwhelming because it's pretty obvious what we're working with. But as you'll see when we start scrolling through, getting to those heavier elements that have lots of energy lines, this can be very helpful because it shows you where they should be at. So if you see 3 or 4 lines in an area, especially with the tins, the leads, all those guys, this will help you identify. Again, especially for you know, your undergrad or students that are learning and trying to get a feel for all these peaks. So while we're talking about that, I want to come into the properties of my spectra. As I said before, remember, properties are our recipe on how we're dealing with things. So you see we have our acquisition, how long we want to collect that data, what elements we've identified, quantitation, which we're going to come back to in just a second, but the next one over is our display. So I want to look at our spectrum display, and you see here we have our custom MLK setup. Our software guys have a sense of humor with MLK instead of KLM. We go to setup. Right now, I have it set to show me all labels and all markers. I'm neurotic. I want to see them all. I want to know what's going on, especially when I'm working with those heavier elements. But you see, I also have the options to scale my markers to the parent peak. As you guys know, again, transition metals, some overlaps. This is going to help us identify if somebody's K alpha is hiding in somebody else's K beta. because it helps me know how tall that K beta should be according to how high up that second line goes, that K beta line on that peak. So this idea of properties, again, how these things are run. If you see at the bottom here, we have safe settings. So let's say you as the expert, you have 500 samples you want run the exact same way, and you have your undergrad, your minion, your intern running them for you. You as the expert can come in and set up how long to run, what elements to identify, how to quantify, even what you want it to look like, and then save those settings with whatever name you need it to be, you know, sample type or your name, whatever it is. And then when that undergrad, minion, intern run samples for you, all they do is load settings, and they use your settings. That way you as the expert knows everything was run the same way. Also, if you're using it, saves you a lot of time. You just load those settings and apply it to everything you're doing. So let's go back to quantitation for a second. The easiest, most straightforward way of doing your quantitation is collect your spectra, label your peaks, and then hit that lightning bolt. That is going to be standardless ZAF quantitation, just really straightforward, just tell me what the heck it is. So if we were to do that, hit our lightning bolt, gives us our data right here. If we need more information, more flexibility in our quantitation of our properties, if you know enough about your sample, you can have it automatically quantitate after you acquire. So if you don't need to identify peaks, you just have it set up and just boom, 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 you're running samples. You can have it do that. So right now, let's look at this. This is set to our default parameters. These are going to be the more common settings for most users. The number of smooths, you know, what background method, what deconvolution method. These are going to be the pretty much work for everybody. Again, everything in our software can be edited. So as you guys, higher level expert users, these things can be set more specific to what you're doing. If you're doing maybe some experimentation, if you're tilting stages, things like that, throwing in weird samples, you can come in here and edit. So it's the option to remove escape peaks and some peaks. So those are those artifacts we're talking about. If your dead time's too high, or maybe you're working on a steel sample that's 98% iron, and you expect to see some peaks, our software can help you account for that. And then also remove it when you do that processing. It's going to remove it from the visual spectrum, but also put those counts back to the peaks that they belong, from where they should have come from, but your detector couldn't process it fast enough. So this is not only visual, but mathematical. Then our background, again, automatic is going to work for most people, most scenarios, but if you guys want to get squirrely, you can come in and mess with some stuff. We have models and filters. We also have files. So this one is where you can save a spectrum as a background and use a spectrum that you've collected as background removal. If that's something down the road you guys might be interested in, you know, if you have a particle, tiny little particle sitting on top of something else and you are in danger of kind of analyzing through it to the substrate, you can save that substrate as the background. I can give you a real quick printout of how to use that. It's very easy to use. Also, deconvolution. We have Gaussian and integral. Again, Gaussian is going to be your more common. We recommend that. We recommend using our default settings. If you want to get in and get fancy, you can. Geometry detector, obviously IXRF, you guys don't have to worry about. These should be set up according to what you guys have. And then we finally get to the meat and potatoes, quantitation. So again, we have ZAF, either with or without standards. You have FIRO-Z, those are going to be for your lighter elements. That's less commonly used, but still used. Again, you guys are welcome to use anything you want. We also have least squares. So that's going to, sorry, I keep bumping the mouse, least squares. That is going to allow you guys to create your own calibration curves, so that if you have multi-element, multi-level concentration standards, or reference standards, intel standards, whatever you want to call them, you can create your own calibration curves for a variety of elements instead of just the ZAF one-to-one comparison. We also have match. This one's kind of a cool one. The way I used to describe this is, say you have a production line where you have 15 stops along that line where at any point one of those stops could potentially contaminate your end product. You can go to each of those 15 stops, collect a piece of metal from them, and sit and collect those spectra and save them in a folder, which we'll lovingly call a library. And now I have an end product. Oh no, it's been contaminated. But which part of the process contaminated it? Now I can run my contamination as an unknown, but instead of asking it to do ZAP and calculate concentration, I can ask it to match. It's going to match to that folder of all of those spectra that I've collected from those 15 stops along my process. And it is going to give me the top 10 closest matches with an associated chi-square value, so I have an idea of how close it's matching. We can even take it one step further, that it identifies the closest match and then uses that match as the standard. So there's quite a few ways that you can use match to apply to the process. This one, these two, you don't have to worry about again, because these go together if you have XRF. Those are for people who are doing dual panel quant. So let's go to advanced. In our advanced window, you'll see we have two different sections. Up here we have component, and down here we have element. And right now they pretty much look the same. We allow you in our software to, again, if you know enough about your sample, you know that you're working either with oxides or with salts or whatever the compound is or component is. You can process as a component and get component data and not just elements. So that can be as oxides. I don't know if you guys have any hopes of working with oxides, but we do have, if we go into our oxide setup, we have the more common oxides. We know there's a lot of interesting research out there, so there may be things that we don't even know is out there. Again, these can be edited to what you may be working with, or you can stick with our common guys. If you do want to work with oxides, to do that, you select your main contributors or your main components here. You see we have arbitrarily these guys. When we go to convert to oxides, it's going to say, okay, you've told me these elements are available. Which ones do you want to use as oxides? Well, I'll use those two guys. So when I select OK, you're going to see my component table is going to change. So now we have the oxides up here, and we have the individual elements down here. So now we'll come back to this quant window, but just quickly so we see oxides working. I'm going to close this. I go to my display. I want to make sure that I'm displaying components and units. Because you saw here, now we're going to process. My lightning bolts process, or over here, analyze. There's two ways to do the same thing. Oh, doesn't want to give me there we go. Concentration is helpful, not just units. There it is. So what we're doing is, as we know, the lighter elements are a pain in the booty to properly elicit. They don't have a lot of electrons to spit off. We're going to probably overcompensate for them. So we do the backwards stoichiometry for you, and that's what's going on here with the oxides. So just quick pause. I'm sure you guys already know, when you are working with the lighter elements, the carbons, nitrogens, oxygens, etc., you absolutely cannot quantify them without using standards. That's not a function of our electronics. That's not a function of your detector. That is a function of physics, because she is a cruel mistress. We will over or undercompensate for what's actually there. So it's imperative, if you want to quantify lighter elements, must use standards. Have to throw that out just to be safe. So back to our quant table. You see here, again, fully editable. If you want to change what your units are, we default to weight percent, but you can do ppm or millimoles per kilogram. You see here, this is our quantitation file or type that we're using. That was selected. Let me move this so you can see it. That was selected here, so that just defaulted to all the different elements. I feel a sneeze coming on. I'm going to try to, hold on, excuse me. Excuse me. So do you guys plan to do quantitation with standards? Is that something you're doing or hoping to do, or are you mostly doing standardless quant?
Well, that was one of my questions also, because the current system that we've got right now, we've got in Oxford, we're using the Inca system. I was always told that every time we do a session, we're going to put in our case, a copper standard, and do a calibration, a quant calibration at the first, at the beginning of that session. And then everything's hunky-dory until, you end your session and maybe somebody else comes on in the afternoon, and then they should do another run another calibration standard against that copper. When we did the install the other day, certainly sort of the big idea was standardless quantification. So that kind of goes against what I've been doing, although I've got another user who says that they don't usually do standards down at their area either. So
Okay.
what's
there's a few different words that we're throwing around when we say calibrations and standards.
okay?
So when we're saying calibration, we mean calibration of the electronics that are giving you your data. So that's why you want a good aluminum copper standard. And the reason that is I'm going to close this so we can see what I'm talking about. When I have an element, nickel, I want a nice nickel peak, and I want these energy lines to be smack dab in the middle of that peak where they belong. That is calibration of your electronics. That's not a standard. So we're making sure that the peaks are sitting in the proper location. That is calibration. So if your peaks are where they belong when you're running whatever you're running, you don't need to worry about calibrating your electronics on a daily basis unless that's part of your SOPs.
Okay.
We have, government labs or, whatever types of labs that they require a calibration check daily. That's calibration of your electronics. Now, when we're talking about a standard, let's think Alouette chemistry, HPLC, GC, mass spec. You use a standard of known concentration to compare your unknown to.
Right.
Because we're teaching the instrument what 73% looks like. Those are when we're talking standards.
Mm-hmm.
So when we're talking standards against an unknown, you can absolutely do what we call ZAF standard blitz. So that has nothing to do with your aluminum copper. That's purely what's going on with your unknown. So EDS ZAF for the transition metals and the heavier elements is pretty darn good without using a certified reference standard.
Okay.
When it becomes important to use either a certified standard or an in-house standard or just something of known concentration, like I mentioned, is with those lighter elements. Because those lighter elements are harder to properly elicit, we're going to probably overcompensate. And you're going to think you have, 50% oxygen when you may really only have 20% if you do it without standards. So when we talk about standards in ZAF, it's extra important with those lighter elements. That's an industry standard. Like I said, it's just pure physics. So that's when you want to have something to teach the instrument what 20% oxygen really looks like, not what it thinks it looks like. Did that help any?
Yeah.
Okay.
That's good. Yeah.
Perfect.
Thanks.
Sure, no problem. So let's go back here to our properties. Oh, you'll also notice I sometimes I'll try not to do it as I'm teaching, but I can be lazy. We have properties up here, and we have properties over here. But as with most Windows-based software, if you right-click, whatever you have across the top also shows up here. So for me to lift my mouse all the way to the top, it's just so much energy, so I'm a right-clicker. I apologize. Try not to do that too often to you. So let's get back into our properties. So you'll see here, because I'm assuming on your setup, talking to your microscope, it's going to take the KV from the microscope so it knows what it's using. You may have the option to estimate from the spectrum. We give you that option if your sample charges a little bit. As you guys know, you can lose some of that energy on a charging sample, so we'll look at that Dwayne Hunt limit and estimate backwards according to how much energy is actually hitting the sample. Okay, back in here. It sounds like maybe you guys aren't initially planning on using either certified standards or known standards. Did I understand that?
That's correct.
Okay. So for you guys, most of the time, from what I'm hearing, you are going to collect a spectrum, label your peaks, hit the lightning bolt, move on with your life. If you want to do things, like components or oxides, you can do that, but you don't even need to worry about calibration files. So for now, I'm just going to skip over that entire thing. If something changes and you guys decide you do want to start dabbling in standards, give me a call, shoot me an email. I'll give you some documents that explain it and how to set it up. It's very easy to use. So kind of keep that in the back of your mind, and we'll skip that for now.
I mean, I'd prefer not to use standards. I mean, they're just one extra step we have to do. So
Well, it really honestly depends on what your end goal is. If you're trying to see, does this one, does sample A have more or less than sample B, you really don't need standards. If you need to know, does sample A have 32% or 33% nickel, then you're pushing where you might need standards. If you need to know, does it have 33% or 50%, you probably don't need standards. So it's really, what's your main goal? Are you just trying to find out what's in a sample? So you guys will know best if you need standards
Right. Okay.
or not, according to your goals.
Good.
So I'm going to turn my beam back on and get us another spectrum to play with. So while I wait for my beam to come back on, let's talk about the display. So we have our spectrum display. We'll go into display and print settings. This to me important for a few reasons. One, if you absolutely hate red against blue, you can change that. So you just pick what color bars you want. When we say bars, we mean like the energy lines, the energy channels. If you have somebody in your lab that's colorblind, or if you want to put up your rival alma mater just to upset one of your colleagues, you can do that too. Put up your colors. We've had that happen. We've had arguments ensue in labs over that. Down here, this is kind of what's more important, is the print, export, and copy settings. So when we get to the point where I'm showing you how to get your data out and how to do reports, this is how it's going to look when it leaves our software. So I have mine defaulted to have a red spectrum and a white background. This is if you're going to be printing and you need to save ink and these things are important. This is where you come to change that. Also, this display is very important because you'll see our quantitation display. When we hit that lightning bolt, a lot is happening. We're getting a lot of information, a lot of data. This is where we decide how much of that data is shown. So you see when I go into my components table, because we're working with oxides, that's a component or a compound, I want to see that data. If I didn't have those selected, even if I process for them, I would not see that data. Elements table, ton of data. You guys can spend plenty of time looking through and see what's available to you. If this is too much information, you don't want it, you can uncheck some boxes. Even our conditions table, if you want to show, you see here, our conditions that we're showing are KV, takeoff angle, and how long it was collected. You guys probably won't be dealing with mass thickness yet, but material classification we'll discuss in a minute. And then also pie chart. Everyone loves a pie chart. If you want a pie chart, go for it. That's how you get it.
One of the things
Simple
that
check.
Oxford did that I just didn't think was necessary.
Did I hear excitement about the pie chart? Please
No,
tell me I did.
I didn't really like the pie charts in the old software that we had.
Well, you don't have to use them, but
Yeah.
there are some countries in the world that love like visual representation. We won't call them out on it, but they love the pie chart. So it's there. So let's go back to quantitation for a second because I showed you material classification. So you saw all of our options for quantifying, with or without standards, whatever you're doing. You saw match, that we can create a library and have it identify. Another one that I love is called material classification. So I like to use steel as an example when discussing this, but because there's so many different types of steel that can vary. Chromium, it can be 1 to 3%, and it's this type of steel, or it can be 3 to 7%. It's completely different types of steel. Material classification allows you to, without an actual reference standard or certified standard in hand to physically analyze, you can, using a textbook, a COA, a known whatever it is, enter concentration windows, say steel 142, can be, iron 90 to 98%, chrome 1 to 5%. Enter these windows of concentration. So when you run an unknown, if this sounds like something you're interested in, again, I can give you a document to walk you through the whole thing. But when you enable this, when you run your unknown and do that standardless dash, it will look at your classifications, and if the unknown concentrations match any of those classifications you've defined, it will say material classification steel 142. So this is another way of kind of identifying something without actually having to use a standard. So that's material classification. So that's kind of the quick and dirty on quant. I'm gonna go on to how to overlay spectra and how to get your data out, unless we have questions on what we've seen so far.
One question that's come up before, and like on this image that you've got on the screen right now, you're going to export this out. We'll talk about that probably later about saving this and sending it out. But right now, on what you've got displayed right now, we have no idea. In essence, we haven't captured an image. This is straight off of the SEM, right?
Correct.
So right now, I don't have any idea what my sample looks like on this with this spectrum.
Correct, because if you're doing something where you have an image where you need, there's different things going on, there's a chunk of something here and a chunk of something there, that's when it's important to grab an image and put, a marker down or a square to raster over that so that you know where that came from. But I have many, many customers that they're looking at big hunks of steel that are homogeneous. They don't care what it looks like. They just want EDS data. Then they just grab a spectrum, and it's going to raster their entire field of view. Whatever they see on their SEM, that's what's being elementally analyzed.
Okay, so right now, if we just grab a spectrum like this, there's no image associated with this spectrum.
Correct.
Okay.
So if you just go here and do new spectrum, or here where it says spectrum, it's literally just rastering your beam over your entire field of view of your SEM. If an image is important to you, by all means, grab an image first, and then put down a spot of interest.
Okay.
So I would do that, and then I would come here and I say, I want to know who he is.
Because even if we grab a spectrum from an entire SEM image, I've still got most of my users, including myself, are going to want to know, a week from now, what was that image or what was that spectrum taken from?
So if visually it doesn't matter what it is, then it's just a function of naming it. This came from sample 542. But if you need to know if 542 has all kinds of different things going on, then it's important for you to grab an image and do a spectrum that way, unless you want to name it a certain way.
Well, even naming it, though,
even
naming it, we're still going to, I think most of my users are going to want still an image to archive with that spectrum, just so they'll know what it looked like, So
Can you take an image, like just a regular image, like you have there, and do the full spectrum on it as well?
Absolutely.
So
Yeah,
you don't have to
absolutely.
do a point and ID if you take an image, but you could have an image with the full spectrum?
You just draw a square box on the whole image.
You would draw a square box over your entire field of view, so then that way, we'll just do it together. So I'm going to grab a new image. So this is going to be lot 5, and then this is our 17th piece of data we've grabbed from lot 5.
So
I'm going to come up here to my rectangle, and I'm going to highlight the whole area.
Yeah.
So this is 17, and then this is 1. So you see how that's labeled 1. So now from a naming standpoint and an image standpoint, I know who belongs to who.
Yeah. And so in general, for I think what we're going to want to use, everybody's just going to take an image first anyway. We're not just going to look at a bulk, because I don't think anybody
That's
uses
totally how you guys use it, because you have to keep in mind we work with absolutely every single industry you can imagine, and some that may not even occur to you. So we have to write our software in such a way that it caters to everyone. So that's why we build in so much flexibility. So yeah, if this makes sense for what you guys are doing, heck yeah, go for it. If that's going to help you correlate data and remember who belongs to what, perfect. That's a great way for it to work for you guys.
Yeah, good. Thanks.
Sure, no problem. I'm going to close this guy. Open this guy. So if you want an unlabeled spectrum, you see our software kind of likes to help you out. So we've already labeled some stuff, and then we collected more spectra, so it assumes you're working with similar items, so it remembers those elements from the previous spectra. If you want to clear a spectra out, you see this guy up here, it says clear element list. It's just going to clear that off for you. So it thinks it's helping you out by remembering stuff, but if you don't want its help, you can just clear those off. I will touch upon this because everyone asks, yes, we do have auto ID. Yes, you may use it, but you need to use it with caution. As with any auto function on anyone's software anywhere, it has sensitivity levels, which can be edited. So you can have it very sensitive to make sure you see trace elements, or not very sensitive where you may lose those low-level elements. So if people are using auto ID, I always say absolutely use it, but double check your data and use your brilliant human mind and eyes to verify what it is ID'd makes sense. Because if it's set too sensitive and I didn't collect many counts and I hit auto ID, it might pick up all kinds of weird stuff that's not there, or it could work beautifully. So right now, I don't have too much background. I might be okay with most of this. If I have it set too sensitive, it might pick this up as a peak, and it might not be something. So just, again, if you want to use auto ID, just use it with caution. I'm going to clear that.
Which button was that?
This guy up here that has the question mark on it, auto ID.
One question that came up during the installation, our
Sure.
old system, as you're collecting, as you're actively collecting a spectrum, as the peaks were starting to grow, it would auto ID automatically as the peaks were going, so it would kind of give you a real-time sense of what the peaks might be, and you could just glance at them and say, oh yeah, I know what that is, and just stop the scan. As opposed to waiting until the entire spectrum finishes and then doing all the ID on it.
Ours won't automatically ID peaks for you as they show up, but here, I'll just start acquiring a spectrum. You, as human, as you see something, you can identify things as they are showing up on your own. You don't have to wait for something. You can see I'm collecting this live and identifying live. And then I can say, oh yeah, and I can stop it and say, that's good enough.
Okay.
Also, what you can do, and you'll see this, if I have labels already there, do you see that?
Yeah.
So that's just remembering labels. So let's say that you're working with something and you're like, well, I'm expecting it to be a stainless steel. So you slap on a few things that are indicative of stainless steel so that as soon as you see those peaks fill the predetermined elements, then you've already answered your own question.
Okay.
One thing I do want to caution you of, I don't know if you noticed what I was doing. I'm currently in a spectrum. If I come up here to new spectrum or over here to new spectrum, it will open a new window. If I just select acquire, it will start to overwrite my data. Now yours probably has a warning label. I think my boss doesn't like our warning labels, so he told it not to work anymore, but yours should have a warning label. Hey, you're about to overwrite data. So just be aware of that.
Okay.
I think, like I said, I think he shut our warning off. He gets annoyed at looking at it. So, what I was about to show you is we've been running maybe a few samples. Now we want to compare them to each other. The easiest way to overlay is if you have the spectra that you're interested already open, you can minimize the windows. So you see that we're not big on fixed windows. I'm a multitasker. I like to see what's going on, move windows around. So let's say I want to overlay this spectrum onto this spectrum. I'm going to hold the control key on the keyboard and my left mouse. So control, left mouse. Do you see that little box that pops up?
No. Do it again.
It's right by the mouse, so I'm going to control. Oh, hold on. Don't look, because I was holding on to it. So control, watch my mouse. Left mouse. Do you see the box? Do you see my mouse?
I see your mouse.
But it just looks like
See
a
the
mouse.
tiny little box that popped up next to my mouse?
No.
No.
Weird. It's there on my screen. Well, okay, so you will see this on
Oh,
your
there it is.
I see a
Yeah.
plus sign there.
There's a.
Okay, you found it?
Now there's one. I think, yeah.
Perhaps there's a lag in the
All
video.
right.
Either that
So
or-
that means I've grabbed this spectrum. So now I can drag this over and drop it on top of another spectrum. So that's one way to overlay. Or I can come up top and say overlay spectrum, and it's going to allow me to open spectrum that I previously collected, and I can say open, and it will drop it on top. And that one's a terrible one because there's barely anything there. It's over here. So we'll go to this one where it's overlaid. So I'm going to maximize that. So you see in the upper right-hand corner, it tells me what spectra is currently overlaid, and it shows me the color. If that's a hard color to see on your screen or for your eyes, you can right-click Again, right-click happy, you'll find so much fun stuff in our software. Change the color, so now you can see that overlay. Okay, so that's an overlay. Wow, my backgrounds, they're not anywhere near each other. How the heck am I supposed to be able to compare these? So we have to normalize that background. To do that, now think of what we're working in. We're working in overlay, so we go back to the overlay menu, and we go to normalize. Now you see this little window open, this normalization region, it defaults from 0 to 10. Well, that's not going to do us much good because we have all of our peaks in 0 to 10. So I can either numerically select a region to normalize to, or I can use my cursor to what we call paint. So if I use the right mouse, I can drag it and you'll see it will unpaint. And then with my left mouse, I can highlight or paint the area I want to normalize to. So the more common way of normalizing is normalizing a region of background where there are no peaks present. The most common way that's going to work best for you. The only time you would want to normalize to an element is when you have two samples that you know for sure beyond shadow of a doubt that have been spiked with the exact same element at the same concentration. So generally, you use an area of background, no peak. Once I've selected that region, you see my numbers have changed from 4.8 to 5.7. I say normalize. Now do you see my background's dropped, and that looks like it makes some more sense. It is important to close this window when you're done normalizing because right now when it's open, my cursor is a tool to paint. So if I go to use my cursor to zoom in, I'll start painting like a maniac. So I'm going to close this, and now I can use my cursor to zoom in. All right, how do we feel about Spectra?
Good. I feel good.
Much better.
We feel jazzed? We excited?
Better than I did the other
I
day.
feel like I actually could go in and take some Spectra now, whereas the other day we had no idea what we were doing.
We were in trouble.
Yeah.
Oh, well, this is progress. This is good. This makes me happy. So now we're going to move on to maps. And even though maps is a really heavy lifting function, you've learned all the hard parts. You know how to work with images. You know how to work with spectra. So maps is just a whole bunch of spectra that make a pretty picture. So I'm going to close all these guys, and we're going to go play with some maps. So I'm going to go backwards in our wizard, work with X-ray maps. I'm going to do some sneaky stuff, so don't watch what I'm doing. I'm going to be sneaky to make, okay. All right, okay. So remember when we said this fast map guide, that's going to map my entire field of view, whatever I'm looking at. So if I start here, acquire a map, or up here, acquire new fast map, I click on that and it's just going to go. So right now, all I have is an image. Great. You see down here I have a sum spectrum. This is my sum spectrum for everything I'm looking at. So like we just learned with spectrum, I can use my cursor. I can zoom in and say, hey, I found a peak. Let's label that bugger. Do you want to add a map? Yes, I do. As you can see, I am adding maps live on the fly, elemental maps. I'm selecting them. So I don't need to know what I'm working with before I start a map. If you do know what you're working with, that's great. You can pick your elements in advance, but you don't have to. We can just let that run a bit. Come in here, let's find somebody else. Sure. Add that. So you can see what I was doing is I'm just zooming around, adding elements. You saw when I added an element, the peak changed color. That's our region of interest. That's the area that we're using to create that map. That's why these change colors. Green is aluminum, aluminum is green. Silicon's blue, silicon's blue. Nickel, red. So it all makes sense.
So when you clicked on a peak, it automatically brought up that box to add the element.
So when I clicked it on down here to label that peak, so I'm going to cheat and use my K alpha. I say, okay, it's cobalt. Do I want to add it? You know what? No, I don't because it's really not there.
Okay.
And now I can remove it.
You could also do that using the right-clicking on the IDs below.
You can double click on these guys. Yep.
Yeah, double-clicking.
Yep. You're absolutely right. So this is if you want to, you're curious what's going on, you want to do it live on the fly. But again, you don't have to deal with it this way. If you know what you're working with and you're doing a map because you want a nice, visual representation, I can show you how to set it up before you start. So I'm going to go ahead and stop this because we have enough data. When I ask it to stop, it says, do you want to stop immediately? The data will not be correct for all pixels. So if you select no, it'll allow it to continue the frame. Because think of what we're doing, we're rastering over an entire field of view. If my beam is rastering, I ask it to stop, the rest of my data won't be consistent. So we'll say let it finish, and it's finished. So now we have some data to play with. So if we come over here to review map properties, again, I'm just broken record, how we collect and how we deal with the data. So the first thing we're going to look at is our acquisition. How did we collect this map? We have our points well and our resolution. Our points well, pretty intuitive, exactly how long am I sitting at each pixel to collect that data. This can be in milliseconds or microseconds. And then we have resolution, exactly like you'd think, like a camera or an image, how many points across the top. So we set it to 256 just for the heck of it. These numbers can be absolutely any combination your heart desires. For getting you started on collecting maps with our software, might I recommend never running your point dwell less than 300 microseconds, because it's just going to be too fast and you will not get data. So that's something you might want to write down and put a star next to. Resolution can be anything you want. If you're just really quickly trying to find an element in a big area in your entire field of view, you're like, okay, I know there's got to be a chunk of copper in here somewhere. You can make, keep your points slow enough that you're going to collect data, but your resolution can be low that if you just see one big old pixel of copper, then you have an idea of where that copper is. So when I set up a map, this is usually where I start. I'll let it collect a few lines, see what it looks like, and then stop it and say, oh, I'm not getting enough counts. This needs to be a bigger number. Or, oh, it's too grainy. This needs to be a bigger number. So anytime I start a map, I've been doing them for years, I still start and stop a few times because there's no magic unless you're running the same exact type of sample. Then you would have the magic. You would already know what your parameters should be. So at these settings, this says it should take about 17 seconds to make one pass over your field of view. There are two ways to collect a map. The more common way that I would suggest is to multiple scans. And the reason that is you're not sitting too long in any one area, so that if your sample might charge a little bit, it's not going to be sitting there making the charging worse. It's just going to keep passing and not sit. So that's what this multiple scan is to allow it to keep rastering and keep passing over your field of view. You can, again, set this up to 1,000. If you find a formula that works for you, you wanted it, 500 points, well, resolution of 301 and 10 scans, great. That can be your setting. I like to just keep it at a lot of scans, poke my head in, see how many count, see what it looks like if I'm getting a nice map, and then stop it when I feel like it. You can do it any way you want. Drift correction. If your sample is in danger of charging, not crazy to the point that you're going to, blank out the whole thing, but just a little bit, and floating away due to that charging, we can account for that. Only to a certain extent. Obviously, if it floats too far away, we can't account for that. But this is helpful if you do drift a little bit and you're planning on running a 2 or 3 hour map. This will stop your map before it drifts too far out and ruins your entire map. We also have map recovery. Again, you have summer storms rolling through, you've running something for 3 hours, you don't want to lose it. This will back up your map so that if you do lose, something happens, you don't lose all of the data you've collected so far. Now, this enable drift correction, you need to have it selected before you start the first collection. When you select that, it will walk you through step by step how to pick an area. It's literally step by step, select an area, do this, do that. So we don't have to necessarily go through that for the interest of time if you want to use this. Most samples shouldn't float away enough. If you're trying to map them, you shouldn't be mapping samples that are going to float too far away, but that is an option if you need it. That said, we go to element selection. This is, a few things can be done in here. If you know what's in your sample and you want to select your elements before you start, you can do that here. Not a problem. Also, this is where you can come to change the color of elements. So silicon might be a little bit hard to see, so I double-clicked on the color of the element, and I got this menu. Now I'm going to go to pseudo gray, and I'm going to select a better color. I say OK. So right now, we have it only show the maps individually. I can show them on the SEM image in any combination.
That's nice.
Also, let's overlay a few.
The old system
You
would
see
do
down
that.
here, I've overlaid settings.
The old system would do that.
If I put the
Yeah.
filters to none, it's going to be
Might as well.
pixelated. If that's okay, that's okay. Smooth, you can smooth out those pixels. Again, we're not changing any of the raw data so much as we're just changing the visual representation. That's important. Also, it is important to understand how we collect our maps. We collect a true spectrum at every single pixel. This is going to be a really big deal in a few minutes when I show you map data. But that's important to understand when we're doing the visual representation, why smoothing is okay, because again, we're not changing the data. Also, you can change the amount of transparency, so you can say how much of that SEM image you see behind your X-ray map. So if it's all the way to the left, it's all image. If it's all the way to the right, it's all spectrum. Somewhere in between, you can see a little bit of both. I'm going to take those off. So this is good for when you're trying to understand what's going on with your sample, a great way to visually represent it. But when it's time to get that data out or do a report, the method that I prefer is I come to View Map Data, or if we come up here, that would be View Overlay Elements. So it's either button you want to use. Oh, no, that was the wrong one. My mistake. Overlay Maps. There we go. Overlay Maps. So this is what I was trying to say before I tripped all over myself, is visual representation. So I select the SEM image. I use the arrows to drop it over. Now I want aluminum. I can just drop it over, and our software will default the colors for us. Or if I want to be persnickety, I can choose the colors. I say OK. And then I'm ready for nickel, and I want nickel to be red. I say OK. And now you have that visual representation. And just like we saw with the overlay over here, the same concept applies here. I have my smoothing, and I have my transparency. Now I can either send this to the clipboard and paste this into whatever I'm working with, Word, PowerPoint, whatever I'm working on. What's really cool is when I put this to the clipboard, and I'm going to show you right now, it might take me a second to open have WebEx open the window for me. So I've clipboarded that. Can you see Microsoft Word?
Yes.
Okay, I'm going to paste. This is why I like to use the clipboard, because it shows me my elements in the color that belongs to them, so I don't have to remember. So now we're going to go back. Nope. I also have the option to export. When you export it, it's just going to export it as an image file. It will not tell you what the colors were, so you have to save that as part of the name. That is why I prefer the clipboard option. You can do whatever works best for you. So that's just working with the pretty pictures. So I told you we collect a true spectrum at every single pixel. I go to View Map Data, or up here, that was the View Element Intensities. This is so cool. Right now, we're looking at what are considered intensity maps. So the brightness correlates the intensity of the peak in that area or that spectrum. Generally, that does correlate back to concentration. That's not always the case, as we know. You know, if you have big peaks, they can affect each other, et cetera, et cetera. But if we're just looking at intensities, or we can process the entire map, meaning literally every single spectrum can have background removed, the peak fit, standard list staff. These can be considered concentrations. We won't do that now because it takes a while and we have lots to look at. But I can either put on a spot and I can pick how big I want that spot to be. And you can see, I move all around. I can also do a rectangle, and what is so cool is when I put down a rectangle, it literally pulls out every single spectrum in that rectangle, puts them all together, and I just got a spectrum from a map that's already been collected that I may have run 3 weeks ago, and I just got real data from a previously collected map. So this is why I like to do maps closer to the end, because everything data-wise you can get in other portions of our software, you can get from a map. You saw we can put down a spot, so I can put down a spot, put down a spot, and then when I select save spot, it pulls that spectrum. Now, word of caution, you see this is a really crappy spectrum. That's a really tiny spot, and I did not run this map very long. So again, you have to think of what you plan to do with your map before you start it. If you're collecting a map just to have a pretty picture, then save it until you have a pretty picture. If you're doing a map because you intend to collect data out of it, and by data I mean spectra like this, you need to collect enough data and let it run enough that you do actually have data. So you saw when I did the raster, the square, that's a pretty decent size. You see that's a pretty decent area to collect data from. I got a decent spectrum. But when I was doing a small little spot of 3 pixels, that's essentially no data. So just kind of be aware of what you plan to do with the end results of your map and just determine how long that map needs to run. And that is exactly why some people might run a map for 7 hours, is because once they're done, they want to be able to pull data from it, and they don't want to have to go back to the sample and try to find a small area to pull a spectra from. Does that make sense?
Yes.
Yeah.
Sorry, we all got
Well,
email all of a sudden.
Uh-oh, is everyone okay? Do we need a minute? I don't mind taking a break if you guys need a break.
No, we're good.
no, we're good.
Okay. Was it at least an exciting email?
No, my phone was just dinging, and I looked down at it for a second.
I thought it was something good, like, hey, everyone's getting a raise. We're all getting
No.
bonuses. They're Friday's
Only.
free. Oh, well. Oh, well. So I'm going to show you a few more things that we're not going to dive into, but just kind of, again, keep in the back of your mind that if down the road as you get more familiar and want to get more fancy, that there are tools available to you. So if we go to view, right now, we're looking at our maps individually. That's why that's checked. We just saw what the element intensities are, where we can put down a spot and pull a spectra. We saw how to overlay elements. You see that we can, right now we're looking at intensity maps. So here we have quantitative element and component maps. So if we go to process, we can actually, like I said, process this entire map, and we can do it as individual elements or as components. So remember we were talking about maybe salts or oxides. So that now these maps will stop showing individual elements, and they'll start showing those oxides or salts as maps. You can take it even further and do what we call composition mapping. So we can add a composition. Some sort of rock, whatever. If you have geologists there, I want to do a fancy rock, whatever it is. We select the color, and then you see we have our minimum maximum weight percent, and it will process the entire map and show it as those compositions. You can have, rock, salt, whatever, as compositions. There's a few things we can do once we have the map. Does this seem like it's enough to get you started on maps?
I have one question. If I have to select a particular small area in the SEM image and do the mapping on that, how do I do that?
I'm sorry, you sound far away and it's echoey. Can you either repeat the question, or maybe someone sitting closer to the phone, can you repeat the question for me? You just sound really echoey and far away.
He wants to take the image and then define the map on a small area of the image.
So that's what we learned at the very beginning, is if we have, I shut my beam off, give me a second, sorry. I'm trying to save my filament. I don't feel like changing enough filament today. Give me a second to turn that back on. So remember at the beginning, if you don't want your entire field of view, you have your image.
Beam comes up fast.
And then over here we have our acquire from image tools, and one of them is map on image. So if I don't need my entire field of view, and let's say I'm just interested in this weird guy over here, I can grab that and I can draw my rectangle around just that. So it brings over just that area that I highlighted. That's what it's collecting now. And it's going to map just that area. Also, you see now we're back in the regular mapping section that we just learned how to use, and it's trying to help me out and remember the elements that I've previously selected. Is that what you were hoping for?
Yeah, perfect.
All right. We'll stop this guy. Stop it immediately. Go back to our map. So when we go to save a map, pretty obvious, it's a lot of data, so we're going to force you to save it as our file type. There's no other options because we have other ways of getting, you saw we can copy and export out that data on the overlays. You know, we saw we can pull out different spectra. So when you save a map, just make sure you save your map because you can come back and get lots of data from it. When we save a spectra, let's actually have a spectrum. When we go to save a spectrum, again, force you to save as the data file type, but also you can automatically export it as an image file. So just, it's pretty obvious, pretty intuitive how to save things, what that means when you do it. So I'm going to quickly show you line scans, and then we're going to talk about doing some reporting. Are you guys interested in line scans? Is that something?
Yes.
Yes.
All right, that's it. So you saw, again, like at the beginning, you can do a line scan from an already collected image if you want to correlate it to other data, or if your only purpose is to sit down and collect a line scan, we can go back, work with line scans. Again, just like it's conceptually just like a map. You can look at the properties. You have your points well and your resolution. What elements you want selected, you can pick them in advance or wait until the sum spectrum shows you what's in it. And then you go to acquire. It's going to grab the image for you. And you see here we have two options. You have horizontal or freehand. This guy is going to be horizontal, so you see my weird sideways cursor. Or I can use my freehand, and I can draw. Once I draw the line, it's immediately going to start collecting that. You see down here, again, just like a map, this is our sum spectrum. This is my carbon, aluminum, silicon, nickel. So we'll let that collect.
So this is also taking a spectrum at every point?
Exactly. So, and again, that's why I wanted to show you maps first, because it's built on everything we just learned in maps. Is a true spectrum at every single point, and we can pull data from this. And I'll let it get just a little bit more data so we have something to look at, and then I will show you what I mean.
So it doesn't show you on the image actually where that.
Oh, ye of little faith. I'll show you in just a second. I want to let our data finish collecting, and then we can look at all the data together.
Well, I mean, as it's collecting, it doesn't have like a cursor going across that line.
No, it does not. But once it's done, I can show you what's where.
Yeah.
But you can kind of tell because you know if you can you put a micron marker on it while you're sitting with it. If you use your acquire image and then micron marker and yeah, so if you had a micron marker, you can see the scale there's 120. If you know what 50 is, then you know about how far through the line it is.
Mm-hmm.
So you can kind of get a sense for it just by watching the intensities.
Well,
so if we go
60's about
to
halfway, so.
Ratiometry.
element intensities, it's just like we saw in maps. I put down a line, and you'll see it on all of the elements, but also on the actual line, and you'll see that changing as we go across.
Yeah. Okay. So once it's laid down, then you can cursor through it.
Absolutely. Yep. So that's how data. That was view intensities. And again, like we just discussed with maps, you can process the entire thing, and these will be true concentrations. Now, right now, this is showing a sum spectrum. If you want to show the spectrum of just where the line is at, you would select the show spectrum. So let's keep going. So now we have all of this data. So we go to view line scan. Let's go to overlay line scans. We get this second window. So I can, again, just like we saw in that same idea, I'm going to select aluminum, bring it over. Well, we'll make aluminum green. I want nickel, making blue. So you can see the comparative intensities. And again, they could be concentrations if you took the time to process. Also, we can overlay this onto the image. So that's a little kind of hard to see. So this is why we build. If we remember on image, anything overlaying on an image is considered an annotation. So if I right click in the image, I go to view, edit, not view, edit, annotation. Now I can grab this annotation and bring this up. I can grab this aluminum nickel. If I don't want that, I can, move it around. I can delete it. And then, we can put our KB or whatever else we need. And now all of this can be exported, printed, clipboarded, whatever you need it. And again, when you go to save, you're going to save it as a line scan. Now, the reason we don't give you options to JPEG things out is because there's a few different types of data all in one file type. So that's why we give you the options of things like show spectrum and like that. But the actual data file you save as a line scan. So we've been busy bees. We have lots and lots and lots of data. Now I want to make a nice report of all of this data. There are a few ways to do that, but first let's start with, because I have a variety of data, my best bet is going to be going to File, Create Word Report. Is it opening Word for you guys on your screen?
No, we just see your primary screen. We see the dialog box there. Oh,
there
I
it
see.
is.
Did it show? I know sometimes WebEx, it delays a second or two. So you see my Word now?
Yeah.
All right. So you see I have my data tree. Any type of data that I had open when I was working over on Iridium is available to me over here. So if I select a plus, that means obviously data is there. So I can grab an image, and all I do, I highlight it, and I say place in report. So now that it's here, I have full reign over it. I can select it, I can crop it, I can resize it, I can write notes next to it. Spectrum.
Word in that window. Huh.
Was there a question?
No, I'm just commenting. Sorry.
Okay, sorry. Sometimes I'm hearing voices. I want to make sure they're yours and not my own. So with Spectrum, you see I have my lot 519-1. I have Spectrum and Analysis. If I select the top of the data tree, it will give me the Spectrum and the Analysis automatically. There's my Spectrum, and it's slowly dropping in my Analysis.
So you can really build a report.
As
Whereas
opposed to
Oxford
forced you
just
into
simply
a
whatever
specific
was
one.
there,
Yeah.
put it in.
Or you had to pick and choose like 2 or 3 different reports if you wanted it presented differently. This is really nice, being able to build it the way you want it.
Oh, yeah. Full flexibility.
Yeah.
And then again, once it's over here, if I want, I want to get rid of this stuff, but nobody needs to know that I had an error, or I don't need this guy, I can delete him. So full flexibility. So this is where it gets really cool. So Spectrum, not that impressive. I'm bringing over Spectrum, bringing over Analysis. Let's talk maps. We know we have lots of data in maps. Which one did we actually run? I think that was what, I think. So again, if I select the top portion where it just says maps, it's going to drop over my 4 maps together. If I select the individual ones, it's going to bring it over by itself and bigger so you can see what's going on. Also, if I have a spectrum that belongs to something, I can bring that over. That's the sum spectrum. My intensities. So remember when I drew those on, and those are comparative intensities, that's this data here comparing those 2 locations. Now, this is where I don't want us to get confused. So this is 519, this is spectrum 1 and 2. If I want the actual spectrum, I come back over here, this is 519 spectrum 1. So when you're in maps and it says spectrum, if you look over here, it says spectrum under maps, that means the sum spectrum, okay? So we can keep going. Now we have our fast line scan. We can bring over the image that we collected, and you see it comes over as we set it up with that nice overlay edited the way we wanted. And then also, we can show the individual line scans. And then the sum spectrum.
Can you highlight multiple items at the same time?
No, because it doesn't know which order you're going to want to put them in. Well, maybe. Let me see if it does. I think it gave me an error last time. Oh, look at you, fancy pants. You can. I think that's something they had changed. All right. Good call. So we have our software guy literally in the same hallway as us, and I feel bad for him because anytime anybody has an idea, he has to work on it. We're constantly working on our software. That's one thing that we very much pride ourselves on compared to some of the other guys. We'll call them the other guys. Is we are constantly adding things and improving our software. We're getting ready to release a new ribbon. So you as our customers, when we get pretty new big buttons, you'll automatically get the software upgrade. You don't get charged for that. Okay, so back to reports. That's the meat and potatoes of it. Because it's a Word report, you could put in a header, a footer, page numbers, whatever you need, and then it's Word, so you can save it. Another way we can do a report is if we're just working with a spectrum, we can kind of be lazy and we go to File, Export. So these titles are a little close. So Create Word Report is that big, heavy, lifting, beautiful report we just saw. Export to Word is an easy way to get some data out, and this is when you're dealing with spectrum. So you see here at the bottom it says Export. I want to export what? I want to export the spectrum. I've quantified, so I want that analysis to go with it. And if this spectrum was collected from an image, from what you tell me, that's mainly what you guys will be doing, so you'll want the image to go as well. This will just come as one simple sheet report. It will have the image, the spectrum, and the quant all quickly printed out for you. You can even pick what you want that spectrum to look like exactly without having to leave our software, do anything. And you can have your header or footer automatically in. So that's quick reporting. I did want to show you one really cool feature because you guys have that automated stage. I would assume that we're communicating to it. If it turns out we're not, let us know and we'll make sure the communication is set up. But if we are communicating to your stage, you can go to this Tools. Okay, come on. Obviously a guy named this Robo Stage. We have Robo Stage.
I'm okay with that.
So what RoboStage does is we talk to your stage, and let's say you have a sample the size of a mouse pad, and you have a whole chunk of data you want to get from it. You want to grab an image from the upper left at 5, 10, and 5,000 times mag. Then you want to grab 3 spectra. Then you want to move to the bottom right and grab a map. Then you want to go back to the middle and grab another image at a different mag.
Hold on just a second. We're having a technical issue.
I think the computer went to sleep.
Our screen just went blank, which I can't believe would be a sleep mode because it's been like 2 hours. I guess it could be. Just so that for a very.
On this one.
I'm checking to see if it still shows you guys are on my side.
Was there a finite time for the?
We all?
No, I gave us extra time. We should still have at least another 20 minutes, but it won't kick us off because I'm still holding session.
No signal is all the smart
All right.
says.
We have got gone to seek help from the IT
Yeah,
professionals.
that's
So.
why we have IT.
So bear with us for just a few moments.
Yeah, we lost your screen, and I don't
Take your
know.
time, do what you gotta do.
I don't want to fix it.
May I jump in and ask a question? Hello.
You sound far away too. Come closer.
Yes, sure. And every time when I report the EDX data, they just say, oh, you can't rely on the quantitative analysis. What's the accuracy of the system?
Depends
So
on the
accuracy
detector.
is a function more of the physics. It's not necessarily our stuff because everyone uses ZAF, which is peak fitting, background removal, all that good stuff. The heavier elements are going to be, and there's no percentage because it's a function of your matrix, of what elements are in there. But we all, as an industry, comfortably say the lighter elements you cannot do without standards. I would not feel comfortable going for a decimal place difference, 33% versus 33.2%. I would say I don't feel comfortable giving a percentage because it's very matrix dependent on how accurate it can be.
Yes.
If you're looking for percentages to determine whether or not to move forward with a process or, quality assurance of something, you have to use standards. I mean,
All right, there we
if
go.
you're looking whether or not to sell a farm on something, you need standards. Are you easily able to compare sample A to sample B and say, they're in about the 30% range, but A has more than B? Absolutely.
So it's like if we're working on the unknown compounds, we just know the elements, but we don't know the automatic weight. So if we use EDX to do the analysis of the compound, so we just can't rely on the automatic rate, right? As you said, like 30% accuracy is not kind of high enough to rely on.
So it depends on how precise you need that data to be. I wouldn't feel comfortable giving someone data and saying, sample A has 33.2%, sample B. It's really a function of how precise you need the data to be. You can give people ballparks, but there's going to be some level of error without standards. EDS is very good standardless.
Yes.
But again, depending on your matrix, you can introduce some sorts of error.
Yes, like if we have a compound, it has been oxidized, like at the initial point, it's one chemical compound, and after some kind of process, it oxidized, it become another compound. So if we kind of want to cross-check these two chemical compounds, is that kind of any possible that we use EDX?
So yeah, if you're doing the oxides, when we do the oxides, we do the backwards stoichiometry. So you're depending on the main contributing element of that oxide. So if we're talking about an aluminum oxide, we're counting on the aluminum. We're not looking towards the oxygen because we know we can't count on oxygen because it's that lighter element. So yes, you can use that as in comparison. You can use those heavier elements. When I say the lighter elements, I mean if you're looking at, something with carbon, oxygen, and maybe some other elements sprinkled in, you can't stand alone on oxygen for an answer. But if you're doing something like you said, like an oxide, absolutely, that's good because we're using the main element to calculate that.
Oh, I see. So basically, you mean it's kind of pretty good if we do the comparison, like if you have the pristine compounds, then have the oxide compounds. If you do the comparison, you can get a very clear result. But if
it's very good for comparison. It's very good for standalone as well. So you can kind of test it on your own. If you have a known reference standard, just for fun, because we're nerdy scientists and this is fun for us, is you have a known, a steel, an oxide, whatever it is, run it, just get the spectra, add your peaks, hit the lightning bolt, and that will give you your ZAF standard list. And you'll be able to compare what it spits out according to what's on your certificate of analysis. It should say maybe 40% iron, 10% nickel, and your EDS might get 30% in cent. So you can see the comparison of what it would be like without using standards on something that you should, what you know it is. And then you'll get a feel for how close you can get. But we have many industries do not use standards, and they are comfortable with the results. Again, if you're doing some sort of quality assurance where you need extreme precision, use it with caution. If you're looking for understanding about how much of something's in there and what's present, then yes, standardless EDS will do great for you.
Another comment that one of my professors has told me about mapping is
Yes.
that maps are comparable only to themselves, not to another map. Is that still true with what your guys' software does? Because it's all about
So-
how long you let it run and the number of counts that it gets and all that.
Exactly. So
Yeah.
let's think when we're comparing one spectra to another. If I run one spectra, assuming all other factors are the same, our working distance, our geometry, our excitation, how long it was collected, if all those things are the same, I'm comparing one spectra to the other, that's apples to apples. That can be very well compared. But when we're talking spectra, maps, like you said, if I'm mapping at the same, pixels, the same resolution, the same dwell time, but one map is 2 inches by 2 inches and another is 1 inch by 1 inch, then you're not getting the same amount of counts and data in an area.
Mm-hmm.
So it's hard to compare one map to another. What you can do is pull out data from a map and then compare their, associated spectra. Like,
So
you find a chunk of something.
So in some ways it might be better to take the full map first and then zoom in on a section for like what you were talking about earlier. Instead of taking just that small window, take the full window and then take a chunk out of that map. Would that be a better way to make sure that the small section is accurate to what the entirety would be? Comparable?
It's all going to be accurate. It's a matter of, did you give it enough chance to collect that data? Now, when you're trying to, I think what he's saying when you're comparing one map to another is, elementally you can say, yes, these elements are present, but from a concentration point,
Right.
if you process the entire map, you could potentially also say concentrations. This one has 10% this in this region. And let me take it a step further. Let me close this window. Are you guys back?
We're good
able to
again.
see my
Yeah.
screen yet?
Yeah, we're back live.
All right. So if we, let's go to process composition. So if you know that you have different areas, what compositions they are, they'll tell you what percentage. So let's say I'm not a geologist. I will make up silly terms, so go mock at me if you are a geologist, but our geology customers use composition a lot because one rock essentially can have different types of known compounds, different types of sub-rocks, right? So if I want to know out of that entire map area what percentage is, insignious, blah, 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 it will, according to the compositions I told it, will tell me out of that entire area what percentage. So when you're saying you can't compare one map to another it doesn't give me enough information. It's very, very almost colloquial, basic, step back too far. I need to know more information. Well, what are you trying to compare from those maps? A percentage of the entire map, how much of it is aluminum oxide, or does it have copper? Or does it have 7% copper in this upper left-hand corner? It's really what are you trying to compare, and knowing what you need, you can work backwards the best way to approach it.
Okay.
I know that wasn't an easy answer, I'm sorry.
No, but it's the issue with maps in general and the way that you have to approach them.
Yeah, you almost have to, and that's why I said it when I start something, I start and stop a few times until I get a feel for, okay, wait, this is what's going on. This is kind of what I need. Maps can be automated in the sense you hit go and plug and chug, but you have to keep in mind what you want to do with it once you have it.
Okay, you were talking about RoboStage.
Robo, you have to say it dramatically. Come on, Robo Stage. All right, so RoboStage. This essentially allows you to create a queue to drive all over your sample and just look at different stuff. So I'm going to essentially, you have to keep in mind putting over on your SEM field of view. So when I say spectrum, it's going to grab a spectrum of my entire field of view because we're automating. So that's why this is important. It's not going to function exactly like you want where you grab a picture and then put down a little dot. So this may not work for all of your applications, but this can work for a lot. If you're concerned about seeing a very specific area, and normally you would put down that dot, but you want to use the RoboStage, you can grab a spectrum, but zoom all the way in. You see my magnification change? So that my field of view only shows that small area I'm interested in getting a spectrum from. I can, grab an image. I can change the mag, grab an image. I can do a fast map. When I do a fast map, it's going to be, again, of whatever my entire field of view is.
And how are you setting what the field of view is?
You move your microscope stage.
Okay, so
see
you're
my stage,
physically
my X and
moving
Y
the
is-
stage as you go? Okay.
Yep. So this way you can collect a whole bunch of data, let it run overnight, and have it waiting for you in the morning. If you have a giant sample where you need a bunch of stuff
I don't
from.
think Miller
We
would
can
like
even
it.
turn off the beam after it's done collecting so that you can, again, run it overnight and not kill your beam.
Mhm.
So you see that my X and Y changed because I was moving my microscope stage, but it also changes my magnification, which allows me to collect lots of different images, spectra, maps, etc. Because you have that motorized stage, either within this program or standalone, we can do what are called stitched images and stitched maps. Again, think of something the size of a mouse pad. It's huge.
Yeah.
I want to image it, but I want to image the whole thing at 10,000 times mag. I would never be able to do that in one field of view, obviously. So stitched image allows me to collect multiple fields at 10,000 times mag of that entire sample and stitch them all together. Same concept with maps. I can map an entire huge area at a high mag and then stitch them together at the end after the fact.
How big do those files get?
Well, when it's done collecting, it compresses it into one image or map. Maps are going to get huge. I don't know how huge because that's a function of how big your area was, how long did you collect, all that good stuff, how many pixels. But they can get pretty decently big. Regular maps, let's see what regular maps, how much data they have.
About 300 megs. Okay.
Yeah, that's for a regular map, and I think that might have been a pretty decent sized map. Oh, that was a stitch map. Let's look at a regular size map. That's also a pretty big map. This guy's probably pretty big because I think we did a big stage map on that guy.
600.
That's not too bad for a big map.
And that's in the data file. Okay.
Yes. Yes. I know I just talked at you for a really long time, and I know this is a lot to process. Just kind of overview, is there anything that you really needed to see and I didn't get a chance to touch upon and you're pulling your hair out?
So the things that I use would be the point NID, the maps, the line scans, the what the heck element is this, all of which I think we covered.
Okay.
I don't know about anybody else.
Yeah, I guess those things, it might be interesting to explore the composition.
Yeah, especially for what you did
Yeah.
with SAC 305, if you could tell
See
it
the
if this is
different
SAC
metallics.
305, yeah.
Yep. But I think we kind of went over that
Yeah.
to the point where we
Or at
probably need
least,
to play with it.
yeah.
So that's the thing with new software. Even if I was sitting in the room with you, it would be the same. You're watching me click around. The main thing when you're learning new software, any new software, is don't be afraid of buttons. If you want to know what something does, click, find out, see what happens. That's the main thing with training too, is I know you're not going to remember everything we covered, but you're going to know in the back of your head, hey, I know it can do this. And then you know to go look for it. So I know it's intense. You're probably going to forget most of the stuff we already saw, but just click around. Don't be afraid of it. You can't hurt anything. Because we don't control the Z of your microscope, so you can't slam anything into your pole piece. So we're good.
One thing, so you said spot size of less than 50 was good, or dead time rather, of less than 50 was what we wanted to stick with.
Yeah.
Our old scope, or the old processing system that we used, it almost always had to have dead time of 30%, 20 to 30. Is that something, like, do we have to have a specific dead time, or if we have no dead time, is that okay, depending on the time constant and those other things?
Yeah. You don't have to have a specific dead time. It's when you get too high that it's a problem.
Okay.
It's okay to have 20 to 30%. You don't need to worry if you have 0.
Okay.
This stuff becomes important in when you plan to compare samples to each other.
Mm-hmm.
Because if one sample had a dead time of 30% and the other had none,
Mm-hmm.
that means some of your other settings didn't match either.
Okay.
So when you're trying to compare, apples to apples, you want everything to be as close to the same setup as possible to get the best way to compare.
Other thing, and I just remembered, one of the other things that my advisor has always wanted to do is try to eliminate the low element peaks so that they don't have this big bulk peak from like all the really low level elements. And he says there's something, because he's used this kind of software before, he says there's a way to scale them so they basically get shrunken down to nothing so it doesn't look like there's a peak there. I don't know what he's talking about, but he always got angry when I'd show him a spectra with that really low element peak. Yeah, so I don't know if that's a setting or something.
Okay, there is a way to cheat, and let me get to the spectrum.
Is this what it is? And that's what I tell him, but I
Maybe
can't.
normalizing.
It's his. He doesn't like that low element peak showing up
It's
on
just
the spectra.
it's
It's
down that
the-
end. It's at that left end. It's an arm.
Yeah, I know.
I probably just
But
said
it's
when I
Bozak.
explained it to.
Well, and okay, I understand. Goodness. So I'm not one for severely ignoring real data, but I understand because it's, if you have heavier elements, you're going to have a whole bunch of stuff that's, all of their, maybe their L lines or whatever, depending on what element is, it's going to be a whole bunch of smattering.
Yeah.
The only way to cheat to do that would be to, when you give him a spectrum, literally zoom in,
Scale it.
move it over so he can't see it, and then do like edit, copy, spectrum, and then paste it somewhere so he can't see it that way.
Okay.
Because we literally, with the threshold settings, we can have your spectrum cut off, but you're in danger of seeing things that are really there, like carbon or oxygen. So you don't want to cheat to the point that you're not allowing it to collect this low energy. You can change, here I can show you right now, even if I go to edit, copy spectrums, and then I'm going to open Word, so bear with me for a second while this opens on both computers for you guys. Can you see my Word?
Yes.
Yes.
Okay. So when I make my own reports, that exact question, sometimes I might have, you see that tiny red line on the far end? That's a low energy noise that I just haven't calibrated properly to get out of my way. Somebody else was working on this instrument before I came in this morning, and they will have their neck wrung, but that's neither here nor there. So what I would do is come and literally crop it. I would just crop that end off so we can't see it. But then, of course, you're in danger of people noticing your markers if you crop it, and they're like, where did 1 and 2 go?
Yeah.
So I understand his annoyance with it. Maybe what you can do is, instead of having every single energy line show.
You said there was a way to remove the low energy peak that you said a second ago, other than like by calibration.
So literally just hiding, zooming in, scrolling over, and hiding it. And then you can, edit, copy out, and paste it somewhere else.
Yeah.
But then your units are still missing down at the end.
Yeah.
Yeah, I mean, if he does he not like seeing like all kinds of crazy outlines? Because you can come to your.
The problem usually is that it's that low energy noise, because we typically deal with a lot of heavier elements, and so we end up with a lot of noise from their low energy peaks.
Below carbon.
And so that just kind of backs up and makes this giant peak at the center, which he always has said that he would like removed, and he always has said that he can calibrate the system to do it on his system, so I should be able to do it on my system. And
it is possible, but I'm concerned. I'll show you where that is. So everybody in the room, be my witness. Do this with caution.
Well, if we have to,
You
we're
have to have
recording
the
this so you
spectrum
can show
open
it
to
to
get to
them.
this.
yeah, You can hear me say he wants it this
Here's
way.
what the application specialist says.
She says don't do it, which is why I don't like to do it. Because
Yeah,
it's data.
slippery slope. It really is, but if you go with it, you have to have a spectrum open to get to this menu. It's utility, energy calibration, then you go to manual. We're talking thresholds.
Okay.
And there's no magic number for me to give you because every system is completely different, but you can, what I would do before you touch anything, when you open this window, write down these numbers. You can always get back
would
to
suggest
the
not
proper
doing that.
calibration.
Yeah.
This is real dangerous.
Yeah, this is the window that, because he showed me this window before on his system. Now I'm looking at it and going, yeah, okay. All right.
It is. So, again, with all the caution in the world,
Yeah.
don't touch a thing,
On his
write
mach-
these numbers
on his
down,
machine,
and make sure you
with
know
him
what
the
time
only one
constant
using
you're
it.
on, because
Yeah.
these can
That's
change
one
a little
thing.
bit for the time constant.
In a core
Write
facility.
it down. That'll always give you a place to go back to try to get better. So then you can mess with your thresholds. What you're going to want to do is you start, I would set your presets like 60 or 100 just because you want to be able to see the changes happen.
Mm-hmm.
When you select acquire, you'll see your spectrum start to acquire. When you make a change, you'll hear our electronics box clicking. That means it's accepting your change, and the spectrum will start over again, and you'll see the change show up. So you'll start to see literally this just disappear.
Okay.
Or if you go the wrong direction, you'll start to see a giant noise peak. That's why it's important to have these written down so you can always get back to status quo.
Okay.
The
So that's
copy
what he's done
calibration
then.
settings button, does that copy to
So
the
what that
file?
is that copies those calibration settings to the different time constants. So if you're working in time constant, you know, what for you guys like 16, and you like those settings, okay, let's back up. You shouldn't need to be in here unless your system needs to be calibrated.
I don't want to be in there.
Yeah, I don't want
Like,
them to be in here.
You don't want
Miller doesn't want
same
us
for
in
everyone
there.
else.
It's
If your system is out of calibration, you know, you've noticed that your peaks aren't lining up, like you know for sure that you have iron in there and your iron is a little too far left or whatever, you're out of calibration. What I tell customers, if you're close but not perfect, so your iron is in the iron peak but it's not perfectly centered, that's close but not perfect. That means you can do automatic calibration.
Mhm.
Email me or call me first. I'll give you a really easy document to walk you through how to do this so you don't hurt anything,
Yeah.
or yourself for that matter. And you do the auto cal. That's when you're close, not perfect.
Yeah, let's just
When
come.
something
we're good on that
catastrophic
one.
happens,
Let's
and
just
you're
come
nowhere
out of
near
this
where
box.
you need to be.
Miller's panicking.
Yeah, why don't we just close that box, okay?
Okay.
There
Well,
you
if it
go.
makes you feel any better, you can password this box so that you can tell your professor that I'm not allowed in there. It's locked.
Yeah. And then he can go talk to you, Mike, and
Yeah.
I'll let him deal with you because I don't want to cut data out. I don't like cutting data out.
Yeah, what you can do is if he doesn't like all of the labels, because the labels can get very hairy. Because, like, you know, if we have that big chunk on here, you have, like, even if you have 3 or 4 of the heavier elements, you're going to have all kinds of crazy label lines. This is where you can come in here and say, I don't want to see any of the M lines, because those are going to be your, or L, depending on what element you're working with. You can take those lines away, so the peak will still be there, but you won't have, like, 25 energy line labels.
Okay.
Would that help?
That'll help a little bit, I think. Yeah.
Okay. I'm sorry.
It's just the quirks of advisors.
I preach on preacher. I have survived the grad school pain.
Is
The
it
best part is when you have a grown-up job and you see them again and they have to actually talk to you like an adult. It's awesome.
is it possible to always keep the dead time 0%?
No, you don't need to. It won't give you any benefit because if you're at 0%, it's highly likely you're not producing enough counts to get good data. So it's okay and comfortable to be in that 10, 20, 30%. Definitely below 50. 0 isn't necessary.
Well, necessary. I mean, if you do the comparison, like for my case, like, so it just kind of keep constant, right? The dead time. So which, as you said, it's not going to be the same setup for the two comparison if the dead time is changing.
So if you're doing 2 comparisons and all of your factors are set the same and you're comparing 2 similar materials, their dead times will therefore also be the same. So if I'm comparing 2 pieces of aluminum that, you know, with whatever else spiked in them, and I'm running at 20 kV at a working distance of, 11, at whatever spot size or probe current your system is set on, those are all the same, then your dead time should also be the same. If you're comparing similar materials with similar settings, the dead time therefore must also be the same. Because remember, all of these factors are a function of each other. Dead time is a function of your time constant and how many counts you're throwing at it.
That's pretty weird because the older system we even have same working constant, same current, same voltage, so the dead time kind of shift vibrate a lot, like at least 10%, which kind of concerns me a lot.
Well, that might be a function of the calibration. Is if you do have low energy noise, that will show up as counts per second, even though it's not your actual sample, it's low energy noise, and that will give you a higher dead time. So if you're switching between time constants and you're seeing huge swings in, if you don't change nothing else but your time constant, you're seeing huge swings in counts per second, that may be because you have low energy noise that needs to be addressed. Now, like I said, with silly detectors, sometimes as they get older, there may be some time constants that just won't work well on your silly. You may get 32, 16, and 4.
So I don't think we pay
and you
that
may
much
lose
attention to
8.
time constant at all.
On the old system.
On the old system, we don't pay attention to time constant. I'll have to go back now and look and see if it's even, well, it's not hooked up right now, but also if you've got charging going on, you're going to have more background, you're going to have, so it's sometimes difficult to compare samples.
Oh, absolutely, and that's unfortunately the nature of the beast. You have to do the best with what you can. It's definitely not a perfect analysis method. Once one of us finds a perfect analysis method, we are going to rule the world. But until then, there's give and take and caveats for every method. It's just it stinks, but it's life, unfortunately.
So to be precise.
So we have to do the best with what parameters we can set to, and then that's why even in the best setups, it's still not a perfect comparison, so we have normalizations that can at least help a little bit by bringing your backgrounds together and help with that comparison. If you're really pushed against the corner, you can get to the point that you're using standards. That'll help if you need concentration. So there's things you can do to help, but it's all a function of what your sample is going to abuse you with.
I totally agree with this because there are times I present data, people will say you can get some idea, but just can't totally count on that.
Yeah.
And the another question was you're talking about the standard. I think like 10 minutes ago. So you say that all our calculations is based on the Zeiss standard.
Yeah.
I'm sorry, somebody just beeped in on my other line, and I missed the most important part of your question. Can you please repeat it?
You're talking about the standard, basically what's the database we use to identify the element. So is that kind of the default database we use, so we don't need to use our own standard? Is that what you think?
So there's not an actual database because the physics, we know what peaks are where, and when we do the standardless quant, it's not against a database, it's against the algorithms of doing that background removal, the peak fitting, and everything that falls under what was considered Gaussian peak fitting. So when you're talking about standards, there's no physical standards built into our system. If you need certified reference standards, that's when you pick a standard that closely matches your unknown. Is that kind of what you were getting at?
Yeah, that's great. I mean, people kind of keep asking that. I just want to kind of assure that. So basically, when people are asking that, we just say it's like default standard we are using. We don't need to calibrate like Dr. Miller said. We use the copper to calibrate the system before we perform another measurement.
But yeah, there's a difference between standards for analysis and what people call standards or calibration standards for the calibration of the electronics. Because we know no matter what, iron K alpha is always going to be at 6.4, whether we like it or not. So if you're looking at peaks or not at 6.4, that means your electronics need to be calibrated. That doesn't mean you need a reference standard.
Even with my copper standard, that's not a reference. That's not a known. I use a piece of copper tape. I assume that's close to 100%.
Because
copper.
you're not looking for concentration. You're looking for element to know where to put your peak.
Yeah.
But with the Oxford system, what we were always told was that essentially do a peak calibration, just to make sure that it's looking for copper, it knows where copper is. So it's looking for that peak around copper. Once you've done that, then it's happy.
So now I
So
don't know.
that,
So it's-
I can't speak to how their electronics works, but that scares me a little.
Yeah.
Because that's telling me that their electronics are unstable, that they need you to check it every single day to make sure their electronics haven't drifted.
Well, it may have been, and we've never had an issue with it over the last
Okay, that's good.
over the last 18 years, and it's
All
probably
right.
something I've held on to just dogmatically, but it was something probably in their protocol they just wanted you to do each time.
So what I tell our customers is, unless you're in some sort of lab that these are your requirements, your your SOPs, your government, you're going up against lawyers, whatever your deal may be, you don't need to check the calibration on a daily basis. You will know if your peaks are not lined up, then you will know that you need to calibrate. If you answer to some governing board, then you may have to, check the calibration once a month, run a full auto cal once a year. I mean, I work with the Secret Service and the FBI. They do full auto cal once a year. They check it like once a week. They check it. They don't do anything about it. They just check it.
Well, in
to
that
sign off.
case, if we're in a forensics lab, I mean, one reason we haven't gone to a forensics lab for some applications is because everything has to be calibrated. The pipetters have to be certified.
Exactly.
Everything in the
Yep.
lab has to be certified. So,
Yep.
we're
Yep.
not to that
Exactly.
degree. We're not to that degree yet. So,
Well, yeah, and that's the thing is, again, what's your end result? Are you going to be sitting on the stand trying to justify data? Well, then you might want things signed off. If, you're just trying to do some experiments and some research and you just need to know what's going on with your sample, as long as your peaks are being properly identified, I wouldn't kill myself every single time I sit down running a little bit of copper.
right.
It's redundant.
Okay. All right. I think we're good here.
All right. Well, what I'm going to do is I'm going to send you some of those quick reference help documents that I mentioned, just so you have them in your arsenal. You also have my email. You are always welcome to call or email for questions. I do travel a lot, so you might get an email response faster than a phone call because I'm often out of the country. Again, you're always welcome to call. You might, if you need a person faster, you can call the main office, or you can call my cell, whatever. Let us know if you need anything. We want you guys to love it. We want you to get really good use out of it and be excited to have it. So keep us posted.
Thanks for your help. This has been fantastic.
Yeah, thank you.
This has been exactly what we needed.
Yep.
Perfect. Glad to hear that. Have fun.
Okay. Thanks,
All
Maggie.
right.
Thank you.
You're most welcome. Bye, everyone.
Bye.
Bye.
All right. Well, that was pretty decent.
Yeah.
All right.
But I definitely think on that map thing with the
I think for
what
ideal
you're
condition for comparison would be if you have single sample with two conditions in it and you can somehow draw the box with.
I would start if you can, depending on how low mag you can go, start with a wide map and then use that little tool that lets you zoom in on a small section of those two maps, because that way you know that all that data was taken at the exact same time under the exact same conditions, and then you can compare these 2 points on that
I think
one
that's the best
bigger
way.
map. Yeah, because I know that you guys do a lot of that with your
No,
stuff.
I actually don't do a lot of comparison. I just use it for representation purpose.
Yeah.
And mostly I get criticized that, oh, you're using EDX, try using something different thing. It's not that
No.
good.
Yes.
But
EDX
there
has
is
a lot of
no
limitations.
different thing, so
Yeah.
it's nice though.
Yeah.
It will help get you some idea about what's inside the sample.
I think best thing is with creating reports.
Oh my gosh.
We can do all the scans
I can
and then
put
create report
everything-
in one.
Yeah. Oh, as opposed to having 6 million files that you then have to go through and take out the pieces that you want. It's not right.
Did Dr. Miller say when we're going to give a try about the machine next time for the next try? Put our hand on the machine.
Sitting down in front of it. I mean, you can go do it whenever. I think based on what we just saw, that
I think
should
it's
be
still
enough
running,
to.
yeah.
See that?
It's up and running. Yeah.
So
Should we try stop and save? Or is that what he's going to?
I don't know. We're gonna sit here and discuss apparently.
Also, it's a card of the webinar.
Yeah, I was trying to. Go ahead. Where's touchscreen? I don't want to do
Oh look, we're close to the
something
meeting now.
stupid.
I can't bring the mouse over there, so.
Sometimes it's a bit light when you touch it. Well, we just let it run. We'll edit later, but
Is there another mouse?
this was all touchscreen because you could go to your volumes of the ceiling microphone and
I don't want to hit exit
I don't
because
want
I
to hit
feel
it.
very
I
afraid
don't
of
want
that.
to hit cancel. That's why I'd rather just let it run until I didn't find him in.
He's not in his office.
Because I don't want to lose this presentation.
No, she did a really good job. I thought it was
He's saving it
very,
to
very thorough. for what
the
we did.
HSOP, what they call deja vu, is a sort of a place where you can put lecture notes. You can put it's all part of HSOP.
Yep.
So this came. That was the.
I want to break it.
So that was just how long you wanted it. Held it back. I mean, he's.
Yeah.
Not
I'm
with
not
the risk,
pushing
yeah.
more buttons
Yeah.
than that.
You know, because if we hit,
Extent.
now we should be able to.
Stop and save.
Not when it could be
Yeah,
I
the
don't
whole
wanna-
entire thing.
that's what that.
The
I mean,
risk
rather than us
reward
get to start
ratio is
pushing
not in our
buttons,
favor.
Yeah.
then it could be. We trash the whole.
Yeah.
Recording it.
All right, thanks for coming over.
Yeah, thanks for
Thank you.
getting that set
That's
up.
good.
That was very helpful.
Yeah, I think now we're.
And I do think
I didn't get 3/4 of that at the training at the
Yeah.
install.
I think if you could get an extra copy of the software, that would be nice because it does save all of the data as the data. And so
See,
if we
that's
could
the
have
thing
it on
is,
a second
you could
computer
say,
that's not the EDS.
Instead of doing all these comparisons while you're setting on the SEM, right?
Exactly.
Yeah.
Taking up SEM time because
Right.
you're being charged $55 an hour.
Right.
Your PIs are. So rather than do all that analysis, what you could do is just simply just crunch out, maps and do then all the comparative stuff. Generate your reports.
Just put it
do
on
all the
another
little,
computer in the
that-
lab.
I
yeah.
liked how you could build a report instead of
Yeah.
just having a cookie cutter sort of. But that's something you can do at your, at home or at the
Exactly.
lab.
Well, if you even just put it, if you had that spare computer in the lab that we use sometimes
Just set it
or
out
whatever,
in the main lab part.
as long as it has the extra
Yeah.
set of software, we can just come in and use
Now,
the
sometimes what they'll
software.
do is some vendors will have the full running version of the software, this Iridium or whatever, and it does everything. Or they'll have that you can buy extra, sort of the stripped down only the analysis part, and it's much cheaper. So
Yeah,
it doesn't
you should-
drive all the scope. You don't need all that back in the lab because
Yeah.
you're not driving anything.
If you could figure that out, that would be.
Well,
a
I'd like
really
to see
nice
at least
thing
Yeah,
to
for
have.
one
how much it
copy, and,
costs,
and I'm sure he's talking about just a little dongle or something on the
Yeah,
back.
it's a dongle they put in the back. Cryptographic key.
And if we could have a dongle that we could, like a second copy that we could just check out, you guys could, plug it in and then bring it back, or again, have an extra
Just have it in the
standalone
lab.
computer in the lab where you could do all your.
I think even if it can read the scans and convert that to Word file, that would be perfect because
Yeah.
that's what we do.
Because that's if you have to leave it and let it do its thing for a while, and then you want to come back and you don't want to sit and analyze all of that data, having another computer that I can just go sit on
Yeah,
and not
and
have
just-
to take up your time or your time on the
'cause then
SCM
we
because
can-
I need to do analysis.
Exactly. Because as long as you're sitting there on the SEM doing all this analysis and generating reports, you're occupying the SEM. So the meter's running.
Right.
Now sometimes they'll cut you deals if you get, one extra copies, $2,000. You can get a site, for like 5 copies. You can get, for it's a little cheaper. But anyway, I'll
That's definitely something worth looking into.
checking into and see if we want to either have the PIs that are interested buy that extra copy,
Yeah.
just chip in, see if
See,
Yeah.
I yeah.
Are you going to share the record of the webinar?
Yeah,
What-
it'll be
the-
online.
yes, what we plan to do is it will be setting on the HSOP server that's here. What I'll then copy it. I hope I don't have to watch the whole thing then to save it. And then save it to my website, to the AURIF website, and then you can just anybody can download it at that point.
I just want to make sure before I put my hands on the real machine.
Yeah.
Just going through one more time.
Because I was taking notes, and I know I'd like to watch it again.
Well, based on sitting down last week and then watching this, I feel a heck of a lot more comfortable with it. And
And even what we went over last week was a little precursor to what she went through.
yeah, not
I
knowing
think
what
it's
those
kind of
tools
similar to the
are.
old software. It's just that the buttons are spread all over the place, and
Yeah.
just try to find the right thing. But
And much of what is in Oxford is here.
Yeah.
Again, it's almost like a foreign language. You know,
I'm
you've got to, you know what you want to say, but you have to translate it to the language you know and then spit it out.
I am almost glad that it doesn't auto ID peaks while you're running, because as we joke, Technetium comes up a lot on Oxford, and it's
I know, it
never
always
actually
comes up.
there. It's just it brings up that peak, and then we just laugh and say, "Oh, it's doing Technetium again. Look at that." It's not there.
Yeah. It's funny how
Yeah, it
It seems to
loves
auto-
to find those. But so it makes it. I'm glad that we can choose the peaks that it starts to look at, but still it'll.
And I don't know if
Give us
there's,
the chance to kinda
if this
ID
is
it.
software is going to be, in all fairness, we've got an older version of Oxford, the Inca system. The new is the Aztec. And so it's a much more robust system like this. So I don't know, in all fairness, if we upgraded to Aztec, would that give us this? Or, because we're buying this outright.
I don't know. I love
Or we're
that.
thinking about it.
I love that word processing stuff. But being able to pick the pieces that I want to send into the Word file. That right there.
And see, I don't know if Aztec will do that. So to be fair, to compare the two, it would almost be, before we purchase this, because we're just on a trial basis right now, is to get Oxford to come in and say, well, let us demo the Aztec system and just see, because since we've already got the Oxford goodies there already, it might not be that much more to upgrade to the Aztec.
or even if we can ask them to give a webinar rather than traveling down here and doing installation and all, it's 2 hours job.
Just
We
to
can
show
all-
the software.
Yeah.
This really
I
I mean,
is.
it could be a
You're
tutorial just
using
like
the
this.
same basic.
We can just say that
stuff
we just
that's
want to see.
Just
what
say,
the scope
okay,
of the
we've already got the
software
Inca system,
Yeah.
and I inherited that Inca system, from engineering, so it was kind of, I've had it forever.
Yeah.
So anyway, again, it might not hurt to get a hold of Oxford and say, although I don't want them to know, we're sort of looking at this too, so.
Well, you could just say we're looking at upgrading.
Upgrade,
our
yeah,
EDS.
just what's
We'd
our
like to
options?
see what-
Show me the Aztec.
Right.
Let's do a WebEx thing.
I think since we have Inca system for, like you said, 18 years, they won't mind spending 2 hours to grow their business.
Oh, yeah, no, I mean, they do it,
Just-
we just have to ask
Just the
that. So.
possibility.
Yeah.
But I think this system's going to run us probably close to 30,000 to get this software. And their box, they've got a box, the computer's there. Now, what they will do is if we purchase the system, right now, just like we are with the Oxford, we're running 2 computers, 2 keyboards, 2 mice, and that whole bit. So if we bought this, they would integrate it into, all they're gonna do is dump, we'd still have the pulse processor and the detector box that's now setting. They would simply take the software, instead of using their computer, would dump it into the SEM computer. And so we would do everything off of 1 computer, 1 mouse, 1 keyboard, the whole thing. And there would be an icon up on one of the screens to launch this. But then you're gonna have all of that screen, you would have to have a third monitor. And so we'd have to, like we talked about the other day, either get a different video card or.
So this is just for software upgrade, not for the detector upgradation.
The detector would stay the same. The detector is the piece hanging off the side.
Yeah.
That's an
Yeah.
Oxford
Yeah, the
detector.
detector hasn't changed.
No.
It's the same detector. It's just the box.
To upgrade the detector would be probably another 60 to 80,000. So there's nothing wrong with the detector part. It's just the software that drives it. In fact, right now this software is using the Oxford detector to just simply gather the counts.
A lot costlier.
Cool. Well, thank you,
All right,
everyone.
yeah, thanks for coming over. Hope you can find your way out.
That might actually be.
Yeah. The easiest way to go that way. You either go. Yeah, you can either go out that way or you go.
Sure. We should say hang up.